All right. Hello, everyone. Welcome to week one. In this week, we'll learn about LLM foundations. And learning this topic is quite important because a lot of advanced applications and use cases these days, for example, agents, reasoning models, writing code platforms, productivity tools, and many other examples are all built on top of LLMs. So our entire focus of this week is to understand how LLMs are built, trained, and work in practice. And in particular, we'll start with an overview. Then we'll talk about the main two stages of training LLMs, pre-training and post-training. And then for each, we'll discuss how they can be performed and completed. And then finally, we have project one, which is a hands-on exercise to build an LLM playground in Python. So let's grab a coffee and start. So what is an LLM? An LLM is simply an AI model that can understand and generate text. Now, if this AI model is trained correctly, it can be very useful because we can ask real questions from the LLM and it can answer to our questions. And then we can also ask follow-up questions and the LLM can respond to our follow-up questions. So it's going to engage in a conversation and it's going to be very useful. Now, there are a lot of different companies that are having their own LLMs and they are providing a chatbot service powered by those LLMs. And one example, popular example is ChatGPT by OpenAI. And I believe that was the first chatbot that made available to public. But following that, there were many other companies having their own LLMs and offering their own chatbot services. For example, we saw Claude from Anthropic. We had Gemini from Google, Grok from xAI, Meta AI from Meta. And I'm sure there are many other examples and many other companies that are offering chatbot services these days. Now, all these services are offering something very similar. There is a UI where you can enter your text and ask a question. And then the LLM would start answering your question. And there are some additional features that some of these chatbots are offering. And some chatbots offer more features than others. But just to get an idea, I have some tabs open here to go to some of these popular chatbot services and and see how they look in practice. So first, we'll go to ChatGPT. Here is the ChatGPT UI. And as you can see, it's a very simple UI. There is a box here where it says ask anything. And here is basically we can ask our question. Here it says ChatGPT 5. If we click here, we'll see a bunch of options. It has Auto, Instant, Thinking, Pro, and there is this legacy model, GPT-4o. And before the introduction of GPT-5, it was a lot more confusing here. There were lots of different options, including non-thinking and thinking models. For example, we had 4o, we had o1, we had o3, and a bunch of other models. So it's a lot more clear now. For now, we'll just stick to their default model, which is auto. So it decides which of these to use. But in future weeks, we'll cover other options. Like we have one full week covering thinking models, and we also talk about test time compute and pro models. But for now, we'll just keep it the auto one. And here, basically, we can, there are just a bunch of tools we can use. It has agent mode, which searches the internet and explores lots of different resources and so on. It has deep research. It has a tool to create image, connectors, and many more tools like a study and learn, web search, and so on. Again, in future weeks, we are covering many of these. We have a week about agents. We have another week about deep research and multi-agent systems, and also image generation models. For now, we are not going to enable any of these tools. And what I want to do is I want to enter a very simple prompt here. So we'll see how it responds. Where is Paris? So when I type where is Paris and enter, it immediately starts to generating text. And this is the text. This is the response. Paris is the capital city of France. It's located in the north central part of the country, and so on. Which seems very reasonable. It gives me a very good sense of where is Paris. And here at the end, it also says, do you want me to explain Paris in terms of geography and location? Basically, it's offering more to me to keep me engaged. So this is ChatGPT and GPT-5. Next, I'm going to switch to Claude. And my purpose is to enter the exact same prompt and see how Claude would respond. This is again the Cloud UI, and you can see it's very simple. It overlaps a lot with ChatGPT. They're just the buttons are sometimes in different places. For example, here is basically where we can choose which model to use. There are different models. Some are more advanced and pro, and we have to pay to use those. And some are their default model. So again, we'll just stick to their default model. And there are some tools here. And then I'm going to write the exact same question here. Where is Paris? And then enter. So it also started responding, and it says Paris is the capital city of France, located in the north central part of the country. And as you can see, this answer is different. It's different in terms of tone, structure, and style from what we saw in the from ChatGPT. And also it's a little bit more detailed. I can see it's providing coordinates like latitude, longitude, and so on. Now let's go to Gemini and ask the exact same question here. So again, here we can choose which model we want to use, and there's a bunch of tools and like deep research to get in-depth answers and so on. But we're only going to enter the same prompt, where is Paris? Paris is the capital and most populous city of France. Again, this answer is not exactly as what we saw earlier by other two models, but this answer is also correct and it seems accurate. It's also providing coordinates. And same story with other chatbots like Grok and Meta AI. I'm not going to enter the same prompt there just to save more time. But it's going to be very similar. Grok, you can choose you see the tools are here and you can choose the models here. And similarly for Meta AI, we can use certain tools and ask Meta AI any question we have. Now, all these models, what they have in common is they were able to respond to my simple prompt. However, they responded differently, and some of them are in more detail, and some are more have different structure and tone. So this is how LLMs are different. Now, if I start asking more complex questions, some of these models may no longer be able to answer my question correctly, and this is why certain LLMs are typically more powerful than others. And it keeps changing because all these companies keep training new LLMs and more powerful LLMs. So the quality of their LLMs keeps changing and improving over time. And again, later we would see how the ranking works and how can we compare various LLMs. But for now, I just wanted to show various LLMs and how they work in practice. Now, the question is how these LLMs are built. And this is the next topic. So LLMs are built typically in two main stages. Stage one is pre-training and stage two is post-training. And we're going to talk about both in very detail in future lectures. But for now, it's at a very high level. Pre-training is basically the first stage of training one LLM. And then in this stage, we train a model using some training algorithm on the internet data. So this stage is very expensive. It requires lots of compute, thousands of GPUs. GPUs are these hardware, basically compute powers that allows us to train LLMs, and they can be very expensive. So it's also a very lengthy process. It requires months of training to train an LLM. And after pre-training stage is complete, the outcome of the pre-training is a base model, which has a very good understanding of the internet data. And in other words, it has implicit knowledge of the world, because assuming that there are lots of text on the internet about all these different domains and different areas. So, and since the model is exposed to all those data, it has a very good understanding of the world and a very good implicit knowledge. Now, the second stage, which is post-training, is basically we continue training this base model on a different data. We call it post-training data until we get the final model. And this stage is a lot less expensive. It requires less GPUs, typically hundreds of GPUs or even less. And then it requires days of training only. And in terms of cost, this stage is less expensive than pre-training. Pre-training typically costs hundreds of millions of dollars, but post-training is a lot cheaper. So only well-funded startups and very big companies can perform and do pre-training, just because it costs a lot. It costs millions of dollars to complete pre-training. There is this interesting report from Stanford, which provides lots of statistics of which companies or which universities have their own LLMs and how much it costs. And I have this open here. There are lots of different statistics. It's an interesting read, like how many models are open and there is no access to the public and so on. And then the cost of some of these models and which the organizations that build these models, you can see all these companies are very big companies that can afford to train LLMs. And then here it shows where like most of the LLMs are coming from industry. And this is also the figure that I wanted to show. Here we have various LLMs and language models. Here we can see the number of parameters, but what I want to focus on is this side, which is the cost, the training cost. Basically, how much it costs to complete training of an LLM. So some of these models might be familiar to you. For example, here we have GPT-3 model with 175 billion parameters, and this model was trained by OpenAI. And you can see the cost of training this model was a little bit less than $10 million, but it's still, very expensive to train such model. And you can see more models here, and then GPT-4 and Gemini Ultra. And if you see these models, they are the cost of training those models are around hundreds of millions of dollars, which is very expensive. And there are some other interesting statistics, but just wanted to focus on how costly it can be to train these LLMs. So back to our lecture. After we complete these two stages of training, pre-training and post-training, this final model is what companies typically use and deploy to power the chatbot service. So for example, if you ask any question from this final model, it would answer. So here is an example. I asked ChatGPT. This is a real example. I asked ChatGPT with a prompt like, tell me a short joke. And then the output was, why was the math book sad? Too many problems. So just wanted to show this example as a way that this final model is what most companies use to deploy and use it as a way to answer users' questions. Now, this is all I wanted to talk about in this lecture. In the next lecture, we'll talk more in detail about pre-training and understand different steps of pre-training. Hey, in the last lecture, we saw various chatbots and LLMs, and then we discussed the two main stages of training LLMs. Stage 1 is pre-training and stage 2 is post-training. In this lecture, we are going to focus on the pre-training stage. And in particular, we are going to talk about the internet data. What does it mean to train something on internet data? How should we collect this data and how to prepare this data? So let's start. So data preparation has three main steps. Step 1 is crawling the internet. So crawling is simply a software that starts from some seed URLs or just a single base URL. And then it tries to extract its content and identify the outgoing links within that URL. And then it goes to those outgoing links. And there is a loop where it keeps doing this. It keeps downloading the content, identifying the outgoing links of various URLs, and then visiting those URLs. It keeps doing this until it visits majority of the internet. So just to better understand how web crawling works, I have asked ChatGPT to write a simple web crawler class in Python. And I also inspected its code. It seems correct. And before talking about the code, the purpose here is not to have a production-ready web crawler software. The purpose is just to understand the logics and understand what are the key pieces in a web crawler. Because once we learn that, most of the advanced web crawlers are all built based on the same logic. So again, any web crawler is just a software. And here we have a simple class, simple web crawler. And what it does is it starts from a base URL, and this is given as the input to this class. And then it also keeps a set, a Python set named visited. And this visited is basically keeps track of URLs that this web crawler already discovered, extracted their content, and it's done. And then we have this method called crawl, and this is the main crawl, the main functionality of this class. What it does is it starts from this toVisit, which is basically a Python list, and it adds the base URL as the first URL to start exploring it. But then this list is basically a way to allow this software to keep adding new links as it discovers them, so it can later explore them. And again, this whole thing is based on a for loop or while loop. And then in the while loop here, we have as long as there are links, unexplored links in the toVisit, meaning that there are URLs that we have not explored this content yet. We extract the URL. If it's previously seen or explored, we skip it. Otherwise, we start the crawling. And here, there are some libraries like requests. Again, we don't want, the focus is not to learn the details of these libraries. There are just lots of different libraries. We can send requests to different URLs and get the output. And here we are using this request.get, send the URL, get a response back. And then from this response, there is this text, which is the HTML content of that URL. Now, again, Beautiful Soup is just one library, and there are other libraries, but all these libraries are allowing us to, once we have the responses, the HTML content, it allows us here to just to go through all the URL links within that HTML content. So here, basically, it says find all these tags, and then those are links, and then if it builds the full link, full URL, because some of these might be like relative URLs. And then once we have that, it just appends them to the toVisit. So basically, toVisit is just a list that it keeps track of all the discovered URLs that we have not still explored its content, HTML content. And then there is a while loop that it continuously tries to explore unseen URLs in the toVisit. And once we are done, it just gets added to the visited. So very simple. So this is the URL. Again, in practice, there are more details, there are more arguments, like maximum number of times to go deep and keep identifying links and going to those links. But those are details. The purpose is just to, for now, understand the high-level logic of building a web crawler. Now, back to the lecture. There are two ways now we can crawl the internet. The first option is to crawl ourselves. And this is what most big companies like OpenAI and Anthropic does. For example, just to validate that Anthropic does crawl, there is this question and it's on the Anthropic website, that whether Anthropic crawl data from the web. And the short answer, if you read this, it says, yes, we do crawl the web. And this is also a GPT-2 paper published by OpenAI. And we're going to talk in detail about different parts of this GPT-2 model later in this week. But for now, I just want to scroll down and get to the training data. Here, training data set. And if you read this, here they're saying that instead we created a new web script which emphasizes document quality. So basically, they are also having their own web crawler. So they have this software, they've written that, and then they're using that to crawl the web. So this is first option. The second option is to use a public repository of crawl pages. Now, there are different research teams and organizations that regularly crawl the internet and provide the extracted content public and make it publicly available. And one very common example is Common Crawl. So I Googled Common Crawl here, and it says Common Crawl is a nonprofit organization that crawls the web and freely provides its archives and data sets to the public. And there is just this website for Common Crawl. If we go there, it's how the website look like. We can go to the data. There is this latest crawl and instructions to get it started. And here we can choose a crawl. And it seems that the crawls are hosted on S3. So here we can just choose crawl. Again, there are various options because they regularly crawl and there are different times. So it's 24 crawls, 23, 22, and it goes all the way back to, I think, since they started 2008. So any of these, once we select, it would just give us some instructions and more details about the crawl. Now, back to the lecture. Most companies prefer to write their own crawling if they are big, so it gives them more flexibility. And for fast experiments or startups or smaller companies, they prefer to start from publicly available crawl pages, just because it allows them to iterate faster. And these are some interesting statistics from Common Crawl. They're crawling the web since 2007, and then each time they crawl, it's approximately 2.7 billion web pages. And as a result of that, there are it's around 200 to 400 terabytes of HTML text content each time that they crawl the internet. And then they release a new crawl every month or 2 months. All right, so this is the step 1 of data preparation, crawling the internet, or in other words, it's collecting data. Now, after we collect this data, the output of that is HTML text content. Now, the second step, which is also very important, is data cleaning. The raw HTML content has lots of issues. For example, here I have a screenshot. If I zoom in to see how this raw data look like, you can see the HTML text content has lots of irrelevant information. For example, there are lots of tags, HTML tags and markdowns and attributes, and many of these are not really useful to train a model. We don't, at least for most use cases, we don't want an LLM to learn about all these tags and head HTML, all these things. What we want is the LLM to learn from the actual content that we see from URLs, the content that we see in a browser. And those are often within certain tags like H1 tags. And here we have the P tags. Like this text, for example, the new MacBook Pro M4 features the latest Apple Silicon. So these are some of the text data that we really want to extract from this HTML content and use them for LLM training. So that is the main goal of data cleaning. It's to extract useful information from the raw HTML content. But that's not the only step to clean the data. There are also other issues in the raw HTML content. For example, a lot of text is duplicated across the internet. You can think of when there is an important news, there are lots of various websites that publish the exact same news or with a slight rewording of the same news or original article. And we typically don't want to have lots of duplicated data in our training data, because if we expose the LLM to duplicated data and the LLM see them over and over again, at some point it may memorize them. So we don't really want the LLM to memorize news. What we want is to learn about different words, different topics and knowledges. So these are some of the things that are important to take care of during the data cleaning. Again, there are other things. For example, one important thing is to make sure that we use only useful and safe content. There are lots of websites that we may not want our LLM to learn from. And as part of data cleaning, it's important to just get rid of those websites and those text content. Now, there are different companies and researchers that they've tried various ways of cleaning the raw HTML content or Common Crawl. And then after they applied those cleaning filters or steps, then they get the clean text and then they name it something. For example, here I have some popular data sets. For example, we have C4, Dolma, RefineWeb, FineWeb. So what these are basically different companies or researchers. We would see them in a bit. They clean the raw data, and then the outcome is just a data set, and then they name it something. For example, they name it C4. For example, if we search C4, we would see under tensorflow.org, we would see the description of the C4 dataset, and it's created by Google. So the description is, this is basically a clean version of Common Crawl's web crawl. So, and then there are more details to it, and you can just read them through and see, how big the data is. For example, how many examples are there in the training split and so on. But what they are is basically they are the cleaned version of Common Crawl. And then this is an example of C4. It's published under it's AI2, and what this is basically how this data looks like. This is not exactly the original C4 that Google published. It's a cleaned version of C4 again. So C4 cleaned Common Crawl, and this is here you can see it's a clean version of Common Crawls. And then this is the processed version of Google's C4 dataset. But again, the whole point is that, and you can see the sizes here, like 305 gigabytes of English data, and the non-clean is 2.3 terabytes, and so on. But basically, the data it's very similar, C4 and here, and also the original C4. After cleaning, it's going to be looking like this. It's a table, and we have some text here. One column is text, and then one column is the URL that this text was extracted from. And you can see here, for instance, this URL had this text. And then there are also more examples, different URLs, different links. And some of these are in different languages. And so this is C4 after cleaning Common Crawl. Now, this data set is relatively old, but it was very important in earlier days of LLMs because a lot of LLMs were using this data set to start from as a starting point to pre-train their LLM. But then there were also other more recent examples and data pipelines for cleaning Common Crawl. One recent example is Dolma. I have the paper here. Dolma, and it says it's an open corpus of 3 trillion tokens for language model pre-training research. And we'll talk more about tokens in future lectures. For now, we can just think of tokens as words or subwords. So what that means is that this, after cleaning the web crawl, this Dolma data set has around 3 trillion words, English words, let's say, or subwords. So this is the scale of the clean data. And then you can also take a look at the paper. It's very interesting statistics here. For example, they're not only starting from Common Crawl, but they're using other sources because all these sources can ultimately be useful for the LLM to learn from. For example, GitHub has lots of code, Reddit, and some other places, Wikipedia. And then these are some numbers and how big the data is and so on. And then you can just read their pipeline and how they clean this data set and what specific filtering steps they apply to clean the web. You can see they have like quality filtering, content filtering, and so on. And there is also another very popular data set. It's called Refined Web. And again, the same story. You can see the stats here and how big these data are. It's basically just a sequence of filtering steps and cleaning steps to clean raw internet data or Common Crawl. Now back to our lecture. So we saw these 3 examples, C4, Dolma, Refined Web. So the last one that I want to share is FindWeb. And FindWeb is more recent and it's openly available. It's published by Hugging Face, and it's basically just a data cleaning pipeline. Here you can see all the details of the pipeline. And I have this screenshot in the lecture as well. These are the key steps of cleaning Common Crawl. And again, now most of these should be familiar. For example, the first step is URL filtering. In this step, they filter URLs that they are not interested the LLM to learn from those content. And there is typically a list of block list content. Here you can see what FindWeb used to filter the URLs, and these are some of the categories. For instance, they filter URLs that are belonging to adult category, and there are some other categories here. And these are pretty it's subjective. Different companies may want to include or exclude certain categories. But again, this is the first step of cleaning the data. So they first just get rid of all the URLs that they are not interested to learn from. And then after that, they extract the actual text from the raw HTML content. This is what we saw earlier, that what we want is the actual text content within certain tags. And then after that, we have language filtering. Here we filter text data from certain languages that we don't want the LLM to necessarily support. And then there are a bunch of other filtering and deduplication. Here it tries to deduplicate very similar content. And then more filters here. And then finally, PII removal. Here they just remove content with sensitive information like bank account, bank numbers, and phone numbers, and those kind of things. And then after they apply all these sequence of filtering steps to the raw data, they end up with the clean data, which has 44 terabytes of disk space. This is the storage needed to just store this final clean data. And then approximately it ends up with 15 trillion tokens. Again, we'll talk about tokens later, but for now we can just think of those as words or subwords. So it's around 15 trillion words. And this is basically what what data cleaning step is. We apply a certain sequence of filters and cleaning steps to go from the raw HTML content to a clean text. And this clean text is basically just a very huge text file, or it can be multiple text files. But again, it's just huge text file that just we have this entire text data from internet. Just to get an idea, this is the fine web data after the cleaning. So this is how it looks like. Again, it's very similar to what we saw earlier. There is this huge table with text column and URL column. You can see from this URL, this text came. And this is the data. This is the final clean data that we want to use to train our LLM. And this is just text from internet. It's very random. Like, did you know you have two little yellow 9-volt and so on? And if you see another example, 5 reasons I love Boston. So basically, it's like a very long text from a huge range of topics and areas and domains that we end up having in this clean text. Back to our lecture, we've covered data cleaning and we saw popular pipelines to clean data. The next step of data preparation is tokenization. The purpose of tokenization is to go from the raw clean data to a long sequence of discrete numbers. And this step is also quite important because machine learning models do not expect textual inputs. What they expect is numerical inputs. So in this step, we follow a certain procedure or algorithm named tokenization to convert text to sequence of numbers. And that sequence of numbers is now useful for the machine learning model or the LLM to learn from. So in this lecture, we covered the key 3 steps of data preparation. We talked about crawling the internet, and we saw that how we can start from some publicly available crawl pages like Common Crawl. Then we saw data cleaning and various pipelines, and how this raw HTML text content can be cleaned using a sequence of filters and algorithms. And then we also saw certain data sets that followed this recipe and pipeline to get a clean data. So we don't have to necessarily write our own cleaning pipeline. We can always start from an open source clean data, such as FineWeb, and we start from there. And then finally, we would tokenize the data to go from the raw text to a long sequence of discrete numbers. So this is the high level of data preparation. In the next lecture, we would talk more about tokenization and we understand how it works in detail. All right. In the last lecture, we learned about the 3 main steps of data preparation, and we saw that the last step, which is also very important, is tokenization. In this step, we convert the raw text into a long sequence of discrete numbers. In this lecture, we are going to learn more about it and we understand how it works under the hood. How can we really build something that can convert raw text into numbers? So let's start. So in tokenizations, we are dealing with two phases. The first phase is the training phase, and then the second phase, which we have it here, is the inference phase. In the training phase, the idea is to expose the tokenizer to this long sequence of text that we've already cleaned, and then we let it learn from it and understand the statistics of different words and what are the unique words. The purpose of the training phase is to apply these two squares that we have here. These are just two algorithms or logics. And then as a result of that, the tokenizer would end up with a vocabulary. So let's just talk about each of these in detail. The first step, the first part is text splitting. So what happens here is that once this long sequence of text is provided, this applies some logic. It's simply a logic to apply to this long sequence of text to split it. Basically, the goal here is to split the text into smaller units. And depending on our logic, it can be implemented in different ways. For example, here we have an example. Machine learning, ML, is a subfield of artificial intelligence. And then after applying text splitting, we may end up with something like this. It's a list of smaller chunks or units of text. For example, we have machine learning, and then we have like smaller units and subfield, artificial, and finally we have dot here. So this is text splitting. Now imagine we apply this logic on the entire cleaned internet data to get a very huge list of smaller units of text. The next part is building the vocabulary. Now, given this huge list, in this step, we create a vocabulary of all the unique units of text that we have in this list. And then we also assign an ID. So it's very simple. Building vocabulary is nothing but finding all the unique units, and we refer to these each of these smaller units of text as tokens. So the building vocabulary is simply responsible for finding all the unique tokens and just listing them in a table, and also assigning an ID to them. For example, we can have a vocabulary like this. And then for tokens, we have a, about, after, all, also, and so on. And these are some of the tokens that we've seen in this list after we splitted the original text. And then these are the IDs, which starts from 0, and we just increment it one by one. And here it can be seen that at the end, we have around 270,131 tokens. And depending on our training data, this long sequence of text, we may end up with different vocabularies with different length. It just depends on how many unique tokens we would end up seeing after we split the text. So this is the training phase. We just run this one time on our training data to build this vocabulary. And then from there, the tokenizer is ready to be used. Basically, the tokenizer, it's just, it internally stores this vocabulary. And then anytime we pass a text to it, it can convert it to a sequence of numbers. And the way that it does is first it runs this text splitting logic. It applies it to tell me a joke. And then it splits tell me a joke to the sequence of tokens. And then it would refer to its internal vocabulary and replace each token with its corresponding ID. So for example, tell me a joke might become tell me a joke after a text splitting. And then after tokens are replaced by their IDs, we may end up with something like this. So this is how a tokenizer can go from any text to a sequence of numbers. In addition to that, it can also go back to an original text given a sequence of numbers. And this is also a very simple logic. So when we pass a sequence of numbers like this to the tokenizer, internally, the tokenizer can also store an inverse table. So instead of mapping from tokens to IDs, it can have a mapping from IDs to tokens. So once this is provided to the tokenizer and we want to detokenize it, meaning that we want to go from numbers to text, it just simply goes to those rows in the inverse table and find the corresponding token. And then it applies the inverse of text splitting to the tokens to output the original text. In this case, tell me a joke. So these are the two main phases of tokenization. And training phase is basically there are different algorithms for the training phase. And all these algorithms mostly differ in their text splitting logic. Because building vocabulary is very obvious. It just needs to find all the unique tokens. Next, we are going to talk about the important categories of tokenizers, which are mostly referring to the algorithm that we can apply here and create the vocabulary. So all these different algorithms, they can be categorized into three big categories. We have word-level tokenizers, we have character-level tokenizers, and we have sub-word-level tokenizers. And again, for each of these, there might be various algorithms within each category. Let's just briefly talk about each. Before I explain in detail, I just want to point out that word-level tokenizer and character-level tokenizers are no longer used in building advanced LLMs, at least to the best of my knowledge. And most of recent and advanced LLMs are all relying on a certain algorithm within the sub-word level tokenization. And the reason for that is because word level and character level has some limitations, which we would talk in a bit. So let's just start with word level tokenizer. It's very simple. As the name indicates, it splits the text based on its, let's say, white spaces to get the actual words. So the text splitting logic is, for instance, split the text based on its white spaces. So a sentence or an input like perfectly fine when it goes to word level tokenization, and word level tokenization applies the text splitting logic, it would end up with perfectly and fine. And then using its internal vocabulary, it would just replace these tokens with their corresponding ID. So these algorithms, when we train on our internet data, we would internally, it would apply this text splitting, and then it would build a vocabulary. And since it's word level, the vocabulary can be very large. And the reason for that is because there are lots of unique words available on the internet, both in English and also in other languages, if we include them in our training data. So you can see here we have perfectly, and then its ID is 52,000 something. And in practice, it can be hundreds of thousands of unique words if we run word level tokenizer on an internet data. So this is word level tokenizer. Now let's switch to character level tokenizer. Again, as the name suggests, it splits the text based on the characters. So for example, an input like perfectly fine, when it goes into character level tokenizer, it becomes something like this: P, E, R, F, E, C, T, and so on. And then each token gets replaced by their ID. And as you can see, the IDs here are very small. And this is because in character level tokenizer, when we apply it, when we train it on the internet data, we don't usually have that many characters. For example, if it's trained on English only data, we would end up perhaps with lowercase, uppercase characters and some punctuations and things like dot and question marks and so on. So the vocabulary length would not be, the vocabulary table is not going to be huge. It's in fact going to be very small, and we would have very little number of tokens. And that's why you see most of these numbers are small here. Now, this is character level. Before I talk about subword level tokenization, I want to talk about the limitations. As we saw earlier, when we run word level tokenizer and train it, we would end up with a huge vocabulary. And that is the limitation of word level tokenizers. When the vocabulary is huge, it means that we have to maintain and manage lots of different tokens. And this can be very expensive when we train a model, because during the training, we have to keep this table and learn some association with each token, or in fact, its IDs. So it's going to be very expensive to learn when our vocabulary is very large. Now, character level tokenizer, its limitation is exactly opposite of that. It does not really suffer from having a huge vocabulary because the vocabulary is small. But what it suffers from is the long sequence of numbers. So, and the reason for that is because of its splitting logic. You can see here, it would end up, after we convert perfectly fine to a sequence of numbers, we would have too many numbers here. And this is not also ideal, and this is also can be expensive, because now during the training, the model need to learn the dependency and the relation between all these tokens. And if this sequence is too long, it's going to be costly. So these are the limitations, and this is why, in the first place, subword level tokenizers were invented and preferred. So now let's switch to subword level tokenizers. So the key intuition behind subword level tokenization is that they come up with some splitting logic, and after we apply that splitting logic to the text, it split the text into smaller units, such that each unit is larger than characters, and also they are smaller than words. So this way, it tries to somehow balance and sit somewhere between word level tokenizers and character level tokenizers. For example, for an input like perfectly fine, after it goes to the subword level tokenizers, it can become something like perfect, Lee, and fine. And then each token would get replaced by their IDs. So as you can see, the tokens are smaller than word level tokenizers. For example, we don't have perfectly as a token. We have perfect and Lee. So the word perfectly would be splitted into smaller units. Now, there are different algorithms that are under subword level tokenizers. And one very popular algorithm is byte pair encoding, or BPE. And that is what a lot of LLMs have been using as a tokenizer. And I'm going to briefly go over it so we get an intuition and high-level understanding of how an algorithm like BPE works. The key idea behind the algorithm is that it starts with characters, and it tries to iteratively merge frequent pairs of tokens and create new tokens. So this way, it has full control over the vocabulary size. Let's see a quick example. I searched online and I found this visualization. This seems to be in Korean. I don't understand Korean, but what I want to show is this diagram. And basically, the way the algorithm tries to form tokens and create its vocabulary is it starts from the training data, it counts all the unique words, and then it gets to the characters. And then for each character, it creates a new token. So for example, H has a new token, U has a new token, and then it stores those in the vocabulary. And then from here, and this 10 is the frequency of basically number of times that this word was appeared in the training data. And then from here, it tries to iteratively merge these tokens. And at this level, it's basically characters. It tries to iteratively merge them and then create new tokens. And the way that it merges two tokens or picks tokens to merge is based on their frequency. So it tries to find the most frequent pair and then just merge them. For example, after here, we have, it creates a new token named UG. And that's simply because there are a lot of UGs in the training data. If you see here, we have UG 10 times. We have also UG here 5 times. And we have UG here 5 times. And because of that, now it creates a new token named UG, because it believes that UG can be a popular token in the training data. And it might have some meanings associated to it. And then it creates UG. And then it continues doing that until it reaches a certain number of tokens in the vocabulary. So it has control over the vocabulary size. Sometimes they keep doing this until the vocabulary reaches, for instance, 50,000 tokens. So this is byte pair encoding, and there is a very interesting tutorial published by Hugging Face, byte pair encoding tokenization. And then here it explains in detail the training algorithm and how it starts forming the tokens and merging and so on. So it can be an interesting read. And then, as I mentioned, to the best of my knowledge, all of advanced LLMs these days are based on some variations of subword level tokenizers, and a lot of them are based on BPE algorithm. For example, in this is GPT-2 paper again. And then again, we are going to talk about different parts of it, like model architecture and so on. But for now, I want to show you the tokenizer that they've been using. So here is the input representation. And here they're talking about byte pair encoding, or BPE. And then they're just explaining it, that how they are using BPE and in fact some variations of it as their tokenizer. And I also searched Llama 3, which is Meta's LLM, and it's relatively new. And even this paper was using BPE as its tokenizer. Here they're saying that the tokenizer is a BPE model. So again, most of the recent LLMs are based on some variations of BPE or some algorithm on their subword level tokenizers. Now, after, just to get a comparison of word level tokenizer, character level tokenizers, and subword level tokenizers, this can be one possible vocabulary after we apply each of these. For example, if we use some character level tokenizer, this can be the vocabulary. And what I want to show here is that the vocabulary is very small in terms of number of tokens. This is an example, but in this case, we have 105 tokens. And then you can see the tokens are like various, like the smallest units of text, which are characters, like A, B, lowercase, uppercase, punctuations, and the space, and so on. Now, if we apply word level tokenizers to our training data, we may end up with a vocabulary like this. And as you can see here, we have a lot more vocabularies. It's 270,000 something. Again, this is an example, but they are closer to reality. And then you can see the tokens are any individual word that was ever seen on the internet. And the reason that it's very, very, this vocabulary can be very, very large is because there are a lot of, on the internet, basically, it's very likely to have lots of random words. I mean, for example, if I search Google something like okay, apparently we have some musics here with this name. And you can see this name. So since internet data means all these text data, and then if we split text by white spaces, we would end up with all these smaller units. And then at some point we would have this sequence of characters as a word. So that's why in practice we would have a vocabulary which can be very, very large, and also not too efficient, because maybe appeared in some few places, but it's not a meaningful word. So it just doesn't, it's not too efficient to have its own token. And then we have subword level vocabulary, which is basically sits in between word level and character level. And you can see tokens can be for important frequent words in English. We have them as their own token, like the, of, home, and so on. And then it tries to also identify the smaller units that are also very frequent, for instance, in English. So that's why we have ing, ed, able, and so on as their own token. So that, for instance, when we have a verb like walking, it can be split into walk and ing. So it's going to split basically text into smaller units. So these are just some examples. And here we have around 50,000, but in practice, in more recent advanced tokenized subword level tokenizers, this vocabulary can be bigger, like 100,000 tokens or even 200,000 tokens. But again, word level tokenizers, especially if we include text from other languages, can become very, very, very large. So that's that. And then the next thing I want to show is an interesting visualization of tokenizers. And there's this website, Tick Tokenizer, and then I have this open here. So this is just a visualization to get a better understanding of how the text look like after we apply tokenization and what are the IDs and so on. So here we can choose some popular tokenizers. So these are basically pre-trained tokenizers on some internet data, and it already has its internal vocabulary. So it's ready to be used for inference. And then these are the names of those tokenizers. So let me choose this one, for instance. And here I can write something like, I love machine learning. And we can see that this has 5 tokens. And then after applying the splitting logic, it splits this text into I, space love, space machine, space learning, and this punctuation. So basically, this is how the algorithm, the BP algorithm, came up with tokens. So the reason that we have a space love is because after applying the algorithm to the internet data, this becomes its own token. And then these are the IDs. So in its vocabulary, I is 40, love is 3021, and so on. And exclamation point is 0. So it's an interesting visualization. We can just play around with it. We can remove spaces and see if it's still a word or not. Or we can do things like, I love walking. And walking is its own token in this example. It's perfectly fine. Let's try this. It's perfectly fine. So here we can see perfectly is becoming 3 tokens. And li, as we had in our example, has its own token. So what that means is, I think I have a misspelling here. Perfectly. All right, now perfectly is its own token. Now, what is interesting, if we try something very random, like it is and something like this, you can see the splitting logic splits it into various smaller units. And that's just simply because we don't have any tokens associated with these words. So for example, is becoming a space and 3A. And then it's, because it's a meaningful word, it has its own token. And there are different tokenizers. We can try different. This one is more recent version, trained and published by OpenAI, O200K base. And then if we apply this, we would just probably see different numbers, and just because its vocabulary is different. All right, and then there are a bunch of other models and open source models. So it's just an interesting thing. And there are different also encodings, and we can also pick models, like actual models, to see how an input prompt gets translated into a sequence of IDs. So this is the visualization of Tick Tokenizer. Now, the next thing I want to talk about is that we saw all these different algorithms, BPE, and how it works. But in practice, we usually do not have to implement them from scratch. There are some great libraries that is already available and open source, and we can use them. And there are also pre-trained tokenizers available. So we don't have to even train tokenizers from scratch if we don't have to. So, and one very popular library is TickToken, published by OpenAI. And this is TickToken, and this is the repo. And again, you can see the code and everything is here available. And it's also very simple to use. We can just basically the description is TickToken is a fast BPE tokenizer. And they have some numbers here that why it's faster than other alternatives. So it says that it's between 3 to 6x faster than other open source tokenizers. So it's a very good library to start from, and use it for our tokenization purposes. And also it's very easy to use. Just to show an example, I have my Jupyter notebook open here, and then I want to show how to use TickToken. So first thing is we install it using just pip install TickToken. And then we can just easily import tick token here and then get an encoding from a certain model. For example, here I have tick token dot encoding for model GPT 3.5. And what that means is that give me the tokenizer that were used for training GPT 3.5 model. And then when I run this, I'll get this tokenizer object. And it's ready to be used. And you can see it's named this. So it's equivalent of what we saw in the visualization, this tokenizer. So after they train the tokenizer on some training data, they just name it something. Now, this tokenizer is ready to use, and it's very simple to use it. We can just say tokenizer.encode, and then write, I love machine learning. And this is the sequence we would get back. And this should be equivalent to what, again, we saw earlier in the visualization. And now we can also decode, meaning that we can go from a sequence of text to its a sequence of numbers to its original text. So now if we pass something like this and call decode on it, if I'm expecting that it would give us I love machine learning. And then we can just add new tokens to see what they are, and then it just keeps changing. So, and then another thing I want to show is that we can write in vocab, and then it would give us the vocabulary size. So this many tokens are available in this tokenizer. And now if I change this to something else, I can change it to GPT-4, let's say, or 4.0. And we saw that GPT-4.0 is the default model when we go to ChatGPT. So let's see what tokenizer it's using. Now, if I print tokenizer, it's the newer 200K base. And from the name, it is probably having higher number of vocabularies. It's probably around 200K. So let's see. Now, let me also rerun this I love machine learning to see if it's going to output the same numbers or not, which we do not expect to be the same. Now, if I run this, it's the same. So at least for these tokens, it's the same. And then if I run this, I would get then it's not the same. So all right, so it's not the same as the GPT 3.5. The tokenizer is different, and the vocabulary IDs are different. Now, if we just copy here and decode it, we would get the original text back. And now number of vocabularies is 200,019. So it's just bigger vocabulary. And what that means is that it's just more advanced and more effective. So this is how easy it can be just to use tokenizers and start from some pre-trained tokenizers to train our LLMs. Now, back to our lecture, we talked about tokenizers and we saw how training works, and after training, how the tokenizer stores its internally and vocabulary. We also discussed the three key categories of tokenizers: word level, character level, and subword level. Word level is problematic because if we have one token for each word, our vocabulary would be huge, and then it's difficult to train on such a huge vocabulary. If we use character level, the vocabulary is small, but the problem is that the sequence of tokens after we split the text can be very large. And also this is going to be problematic when we train LLM because it has to learn all the dependencies between all these different tokens. And if they're a very long sequence of tokens, it's going to be more expensive and difficult for the LLM to learn from. And then we discussed subword level tokenizers, which is balances between these two. So the vocabulary is more manageable and the sequence length is also more manageable. And there were some algorithms, and we saw that the most popular algorithm is probably BPE, and various LLMs use some variations of BPE. And then the way it works is that it starts with characters, and then it tries to iteratively merge tokens, and form new tokens. And then this merging tokens is based on what is the most frequent pair that they can just merge. And that's how they continue doing this and continuing the algorithm until they reach a threshold for the vocabulary size. So, and then we also saw some visualization and the tick token library and how easy it can be to just use some pre-trained tokenizers. So that's all I wanted to cover for tokenizations. And then in the next lecture, we would start learning about model architecture and understand how LLMs look internally. Hello, everyone. Welcome back. In this lecture, we are going to focus on the model architecture. In the previous lectures, we talked about data preparation and wrapped up, and we understood how we can prepare data and tokenize it. The focus of this lecture is to understand now how LLMs look like internally. We'll start by reviewing neural networks and some important layers. And then after that, we will talk about transformer and decoder-only transformer architecture. And finally, we will discuss why transformers are so powerful and widely used for text generation. So let's start. So the first thing is, what is neural network? And before answering that, let's understand the goal of most machine learning models. Most machine learning models are basically trying to learn a mapping from some input to output. I have 3 examples here. And if we look at them, in all of them, we want to learn a model to learn a mapping from input to output. On the left, I have house price prediction. And then we can think of this problem as given some signals about the houses, we want to predict its price. And those signals can be anything like location, number of bedrooms, and house size, and those kind of things. And then somehow they get converted to numbers. There are various ways to encode these signals into numbers, and that's not the main focus of this lecture. But let's assume that there are some ways to convert these to numbers. And then price is also a number. So we can think of the input as x, which has all these x1, x2, and xn for different signals. And then the output is y, which is price. Now, we want the machine learning model to learn a mapping from x to y. So look at all the training data of x and y, learn from it. And then when we give a new x to it, it should be able to predict y. So it's essentially learning this mapping, this arrow here that I have, to go from any x to y. Now, in another example, for instance, email spam classification. And the problem here is given an email, we want a model to classify it as a spam or not a spam. So we can think of, useful signals like sender, content, subject of the email, and so on. And then these gets converted into numbers as the first step. So we can think of the input as x, and then it has all these x1, x2, and xn. And then the output is basically expected to be whether it's a spam or not. So y can be basically 1 if the email is a spam, and it can be 0 if the email is not a spam. So the goal of the machine learning model here is to learn a mapping from x to y. So again, while it's a different problem, the goal of the machine learning is still the same, to just learn a mapping from a bunch of examples with x and y. And then the third example, like a tumor detection. Here, the problem is given an image. We want an ML model to find the location of the detected tumor, if it exists. And even in this example, everything is basically can be converted to a number. And then the model's goal is to learn the mapping. Image can be represented by its pixels. And then location of detected tumors. Tumor can be, we can think of that as 4 numbers. And the top left, basically x and y, and bottom right, x and y. So if it's a rectangle, we just include the top left and bottom right. So at the end, there are just 4 numbers that the model is expected to map to. So even tumor detection is also a mapping. Now, neural network is just a sequence of parameterized transformations that maps an input to an output. So it's just one way that it starts from x, and there's just a sequence of transformations. It transforms x into some intermediate representations, and it keeps transforming and transforming until it reaches the final output, which is y. And those transformations are learnable, meaning that there are some parameters, and then the goal of the machine learning model during training is to learn those parameters, such that for that particular task, it can keep transforming the input in a very relevant and effective way, so that its final output is y. And this is a simple visualization and example. So let's say we have a neural network here, and there is some input to it with 4 numbers, 0.1, 0.5, and 2 more. And then this goes into neural network. Again, internally, neural network has some transformations. In this case, let's assume for simplicity, it has one transformation only. And it just transforms it. So one very simple way of transformation we can think of is that it also internally keeps 4 parameters or weights. And then these weights gets multiplied by the different x values, and then we just add them up. So we can have something like W1 times X1 plus W2 times X2 and so on. So at the end, basically, this neural network is just transforming this using a linear weighted combination of its values. And then the output is going to be one number. So this is just a very simple way of transforming some input to output using some internal parameters. But in practice, it can be more complex. A neural network can have multiple layers, and each layer is transforming its input to some output. And for example, layer 1 transforms x1 to x2 using its internal parameters. And then x2 becomes an intermediate representation, which goes to layer 2. And layer 2 again transforms it. And it goes all the way to layer n. And then layer n transforms its input, and its output can be the final output of this neural network. So again, all I wanted to show here is that neural network is simply just a sequence of transformations to learn a mapping from inputs x to outputs y. Okay, now let's zoom in into these layers and understand what are some common layers in neural networks. So the first layer that is very commonly used in neural network as a building block is linear layer. And linear layer, again, as the name suggests, it's just a linear transformation of the input. So for example, if the input is x, it internally has these W and B parameters, weights and bias. And these are the parameters of this linear layer, meaning that it would learn these during the training time. And then it just linearly transforms x by using this formula. And then it calculates the output y. So we can see this in an example here. Let me zoom in. So for example, if the input is x with these 4 values, what that means is that internally it has to, it's a linear transformation. So we have to have a weight for each of these values so that we can just multiply them. So the weight matrix is going to have a shape of 1 by 4 because the output has 1 number and the input has 4 numbers. And then the bias has just 1 number, and we'll see why, but just at a very high level, after we multiply all the weights with the x and just add them up, then we add it with a bias. So this is just the formulation here. We have this b here. Now, another way we can think of linear layer is something like this. We have 4 small circles here, and this corresponds to the inputs. So for example, inside this circle is 0.1. Inside the second circle is 0.5, and so on. And then we want to go to one number here, which is the output. It's 0.6. And then we have these connections here, and these connections are the associated weights to these connections. So, and since their weights has a shape of 1 by 4, it's coming from here because there are just 4 connections. And then the weights can be named this way, like W11, 12, 13, 14. And now imagine if we had more outputs, like one more output here, we would end up having 2 circles here. And then the weight shape would have been 2 by 4, because now we would have 4 more connections to the second neuron, to the second circle. Now, this is also where the name neural network is coming from, because these circles we can think of those as neurons. And then these connections can be also think of as connections between neurons. So this is how a linear layer transform some input to output. Very simple formulation. And now this can be generalized into more outputs. For example, if the input has more numbers, and then it's expected to produce an output with more numbers also, then the weight can be more complex. If we just visualize it, we would have more neurons, input neurons, and more output neurons. And as a result, the weight matrix would be bigger. It's basically 4 times this many neurons. But this is all linear layer is. It's just basically a weight matrix that is stored internally and will be learned during training time. And then the weight matrix is used to transform input to output. Now, because of that, we can think of linear layer as just a mathematical expression that converts x to y. So at the end of the day, linear layer is just a mathematical expression. And then it can be written down like this. For example, this neuron can be calculated by multiplying weight with the inputs and just add them up. And also more output neurons can be computed in a similar way. So linear layer is just a mathematical expression. Now, linear layer is not the only layer that is available. There are a lot more layers that were developed over the years. I have listed some of them here. For example, we have convolution layers, we have activation layers, we have attention layers, and many other examples. And each of these layers having different purposes and different strength. And they're designed for different reasons. So, for example, convolution layers are designed so they work better with spatial inputs like images. So I'm not going to talk about these layers in detail. There are some wonderful resources out there which you can take a look. But what I wanted to share is that all these layers that are inside neural networks, it's one of these. It can be linear layer, it can be convolution layer. And all these layers, what they differ is basically how they formulate their transformation. They just formulate it differently. For example, we saw linear layer here. It formulates the transformation as a linear transformation. Now, this is going to be different for other layers. So that's how these layers are different. But they all are similar in a way that they just transform some input to output. Now, let's go to the next part, which is basically neural network is just a sequence of layers. We just saw that very early in this lecture. So what that means is that, for example, a neural network does have multiple layers. In this example, linear layers. If we visualize it, it would look like something like this. For example, the inputs come here. We have linear layer 1 weights here. It transforms the input to some intermediate output. Now this goes into linear 2. Linear 2 has this weight matrix here. And then it transforms this intermediate representation into another intermediate representation, and so on. And then finally, the final linear layer transforms its input to some output here, and these are the weights. So we saw that how linear layer is just a mathematical expression. But if we think of this neural network, this is also a mathematical expression. So what that means is that we can write x using some mathematical expression that is calculated using x. And we can just think of that as something like this here. This can be the expression to calculate y's. And you can see it is based on all the weights of linear layers that are inside the neural network. And then it just gets it's a bunch of multiplication and additions, and that's it. So neural network as a whole is also a mathematical expression that transforms x to y. Now, over the years, research teams and companies have tried combining various layers and build a neural network that works better for certain tasks. There was a lot of novelty and innovations into how to combine all these different layers in a unique way that the output, which is the neural network, can learn the task very effectively. And then in 2017, Google published a paper named Attention is All You Need. And then it introduced transformer architecture. And transformer architecture is also a neural network, and it's just basically a unique way of combining all these layers that we just saw, that it works really well for certain tasks. So here is the paper, Attention is All You Need, and it was published by Google Brain Team. And it's just the explanation and how they came up with the architecture and how it looks like. But here in figure 1, they have the architecture of the transformer. Again, feel free to read the paper to understand all these components. But what I want to share here is, at the end of the day, this architecture is also just a combination of layers that we saw earlier. And as a whole, we can think of it as a neural network. And this is basically a unique way of just putting and stacking all these available layers, just stacking them and then training it. So this was the key innovation of Transformer, and it works really well for their task. And initially in this paper, the task that they were trying to solve was machine translation, meaning that they wanted to translate text from one language to another language. So the input here is, for instance, the text in the source language. And then it goes through all these transformations here. And then the output is basically, we'll talk more about the output of transformers in a bit. But the output is basically, eventually is going to be the translated text in the target language. Now I have this screenshot of this diagram here in the transformer part of the lecture. And again, it's just a unique way of combining layers and building this neural network. But at the end, if you think of this, this is also a mathematical expression, as we saw earlier, because each of these layers are some mathematical expression. And then just stacking them together, we still can compute the output based on the inputs. So if we just visualize this, it can be something like this. This image is just is not real. I generated it by ChatGPT. I just wanted to show that even transformer can be written in some mathematical expression. Basically, it can be written in this format. And if you're interested to learn more about transformer and what are the reasons behind each component of it, there is this great illustration by Jay Alamar. And it's a wonderful resource to go through and learn about the high levels and how transformer looks like. See, here is the input in the source language. Then here is the output. I'm a student in the target language, which seems to be English here. And then it talks about all the components, encoder, decoder. Basically, encoder is this part of the architecture on the left, because it's encoding the input text, which is in the source language. And then it has also decoders, which is this right part of the transformer. And it's because now it starts to decode the encoded input text to some output text in the target language. But again, and it goes deeper and talks about all the details of all the components. So it's going to be an interesting read if you are not too familiar with the transformer architecture. So this transformer was really, really powerful for machine translation. And then later we realized that if we only keep this decoder part, meaning the right side of this, it would be really powerful for text generation. And then this is what we call decoder-only transformer. So it's nothing but just the decoder part of the original transformer architecture. So it looks like this. Again, it's just a combination of layers stacked, and some of them are like blocked because these are just supposed to be repeated n times. So we have times n here. So what that means is that this whole is considered a transformer block, and we have n block stacked right after each other. So this works very well for text generation, and LLMs, or large language models, are also a text generation model. So most of the LLMs that I'm aware of are all based on decoder-only transformer. So what that means is that whenever we hear LLM, it means that it's just a decoder-only transformer trained on internet data. So in the next lecture, we'll talk more about the input and output of transformers, and we understand why this architecture, how can it be adapted for text generation. All right, we saw that decoder-only transformer is really powerful for text generation. So let's understand why. And to answer that, let's first see what is the input and output of the transformer architecture. So as we saw in the previous lecture, the transformer is just a sequence of transformer blocks, and each block has some layers, and they're just stacked, and they transform input to output. But what is the input and output? The input that these layers expect is a sequence of vectors. This is just how these layers are expecting their input. For example, here we have one vector, we have three vectors. These three vectors, and again, each of these vectors are having these small cells. Each cell is basically a single floating point number. And so these three goes into transformer. Transformer just keeps transforming them. And then the output of the transformer is again a sequence of vectors. And as you can see, the size of the vectors are the same in this example. And it's in most architectures, it's the same. Theoretically, they can be different, but we just keep them the same. And then the output sequence length is also the same. So we have three inputs and three outputs. So this is the input and output of the decoder-only transformer. Now, let's also understand what is the input and output of an LLM for text generation. So in LLM, again, for texts, they're converted to tokens. So each text is a sequence of tokens. And in order to generate text, what we want an LLM to do is we just pass some sequence of text to it. For example, here we pass these three numbers corresponding to hi, how, are. And then we expect the transformer, the LLM to output the next token. And here it's 944, which corresponds to U. So this is our ideal input-output that we want to train or build LLMs. Transformers are expecting a sequence of vectors. What we want from the LLM is a sequence of numbers going to the LLM, and then the LLM just predict the next token, and also a number. Now, how should we adapt this? How can we really modify and add new layers to this architecture so its input and output becomes compatible with this? Now, this is how we are going to do this. For a given text like hi, how, are, first we discuss how it goes to the tokenization and gets converted to a sequence of numbers. Now, this sequence of numbers goes into another layer. We call these layers embedding layers. And what embedding layer does is it converts each number into a vector. And it's also learnable, meaning that during training, this embedding layer would be learned so that each ID gets converted to a sequence of numbers or embedding that is meaningful or useful or effective for the model to predict the next token. So here, for instance, these three tokens, these three IDs goes into embedding layer, and then the output becomes three vectors. And this is exactly what the transformer expected as the input. So by just adding these two layers, we can easily adapt it to work with our input text. Now, let's get to the output. The output of transformer is three vectors corresponding to each of the three input vectors. But what we want is the next token. So a typical way to make this work is we discard the first few vectors, and we only keep the last vector. And now this last vector is, again, it's just a vector. It's just some numbers, floating point numbers. We add a linear layer on top of this. So we transform this vector into a new vector. And this new vector can be interpreted as probabilities of the next token. So its length would be equal to our vocabulary size. For example, if we have 50,000 tokens in our vocabulary, the output of this transformation by this linear layer would be a vector of size 50,000. And then the value of each cell corresponds to the probability for that particular token in our vocabulary. So basically, this linear layer is just mapping this final output into probabilities of different tokens. And again, there is just also a softmax operation, which is responsible to convert these into probabilities. We skip that for simplicity. But we can think of these layers to convert the final output of the transformer into some probabilities for each token. And now these probabilities can be, we can think of those as something like this. So for example, this entire thing we had here, this tokenization embedding layer, decoder-only transformer blocks, and the additional linear layer here, all of this, we can think of it as the LLM architecture. So here I have this LLM. I hope UR goes into the LLM. And then after the linear transformation, the output is this vector with 5 values here, 5 probabilities. And again, this is only for visualization. In practice, this vector would be of length 50,000 or whatever our vocabulary size is. And then these are associated to our tokens. For example, we can think of this as the probability distribution over the vocabularies. So in this case, if the ID 0 corresponds to end of sentence token, it has 2% chance. For Abel, it has 11% chance, and so on. And we can see the highest probability is well, with 86% chance, which also makes the most sense when the input is I hope you are, because well is the most likely token and also make this whole sentence meaningful. So this is how basically we go from the original decoder-only transformer blocks. We combine it with some additional layers to make it work for text generation and learning dependencies between texts. Now, the next thing I want to talk about is if we think of all modern LLMs these days, they're all based on decoder-only transformers. What they differ is basically some hyperparameters in the decoder-only transformer. For example, this is the screenshot I took from GPT-2 paper, and then they have 4 variations of models, and each variation has different number of parameters just because of the different hyperparameters used to build the architecture, to build the decoder-only transformer. And some of these hyperparameters are, for example, layers. And layers refers to that times n that we saw in the figure, like how many transformer blocks we want to stack. For example, their smallest model, they stack 12 transformer blocks. And then this is the dimension of the vectors, like the input vector size and basically the size of the vector that this transformer works with. And then they use 768 for the smallest model. And they just play around with these numbers to get bigger models. So when they increase number of layers, it means that there are more blocks and more layers, and each layer internally has parameters. So we just simply get bigger models with more parameters. And this generally means that the models become more powerful because when they have more parameters, it means that they are more they have more capacity to learn more complex mappings from input to output. But they are also more expensive to train because if there are more parameters, we have to train them for longer, and we have to also spend more computing power to train these models. So this is GPT-2, and their biggest model has around 1,542 million parameters. So it's around basically 1.5 billion parameters. Now, this is GPT-3. Let me make this a little bit bigger. So GPT-3 is basically the next model that OpenAI trained and released after GPT-2. And what they did was they just scaled the models. So they increased the hyperparameters. So they trained bigger and bigger models with more capacity. So for example, here they have GPT-3 is small and other variations. And their biggest model is GPT-3, 175 billion parameters. So this is very big, and we'll see shortly that working with these big models can be very challenging engineering wise, and it requires a lot of engineering effort so that we can load them and train them and later serve them. But here you can see the different hyperparameters that were used. For instance, for the biggest model, they're using 96 layers. And then the dimension that the transformer is working with is 12,000 something, and more hyperparameters. And also I included Llama 3 from Facebook. But again, the same story, 3 variations. And this last variation here is even bigger than GPT-3. It has 405 billion parameters. And then these are some of the hyperparameters that they've been using for number of layers, model dimension, and some other parameters. So this is all I wanted to cover for in the model architecture. We saw that everything is basically just based on a decoder-only transformer, and they just keep changing the hyperparameters to increase or decrease the capacity of the model. And then typically increasing the number of parameters means that the model would be more capable after training. In the next lecture, we'll talk about how to train the decoder-only transformer model. Hey everyone, let's focus on the model training of LLMs. In the last lecture, we saw how LLMs look like internally and what's their model architecture. We also saw that whatever input we pass them, like I hope you are, it would produce a vector which represents the probabilities of different tokens. However, if we do not train the model, these probabilities would be random. And the reason for that is because all the model parameters are random. So LLM has these layers, and layers are keeping their weights, and those weights are random. So when we pass this I hope you are as a basically sequence of vectors, it goes to the LLM. And remember, this entire thing, as we mentioned last time, is just a mathematical expression. And since all the weights are random, that means that the output would be random. So all the probabilities that would be produced by the LLM are meaningless. So we cannot really use this and rely on it to produce the next token. The purpose of model training is to use some processes and algorithm to tune these parameters that are internal to the LLM. So each layer would keep changing its parameters after we expose the LLM to the entire internet data, such that it can more accurately predict these probabilities. So let's understand this in more detail. So we have this internet data, which is cleaned and also converted to a sequence of IDs. Here, just for simplicity, in my example, I'm just showing them in text, in pure text, just so we understand easier. But in practice, this text and this text that goes into the LLM are basically just a sequence of IDs. So how training works? Basically, we have this internet data, and imagine this is some paragraph somewhere on the internet, and we have something like Albert Einstein was a German-born physicist and mathematician, and so on. So the goal of training is to just expose the LLM to some part of this paragraph, and then we force the model to predict the next token accurately. So what that means is that, for instance, we can just sample some part of this, like Albert Einstein was a German-born, and then we pass it to the LLM. From the paragraph in our training data, we know that the next correct word is physicist. So when we pass this to the LLM, we get the probabilities of the next token. We also know that what is the correct token. So this vector, we can think of that everywhere is 0 except the ID of the correct token, the ID that corresponds to the physicist token. So that ID is 1, let's say it's here, and everywhere else is 0. And these are probabilities. And the goal is to try to update the parameters of the LLM so that the probabilities are as close as possible to this vector. For that, we have to define a loss function. And there are just typical loss functions that are used for different problems. And basically what the loss function does, it measures the quality of the current predictions. So let's say these are the probabilities. Cross entropy loss is the common loss for this purpose that we use. We use that. It's just a formulation to compare these probabilities with the correct token and just would give us a number. And that number, if it's high, it means that these two vectors are not similar. So the loss is high. And if the probabilities are more similar to the correct token, the loss would be low. So this is the first step of training. We sample some text, we pass it to the LLM, then we use a loss function such as cross entropy loss to measure the quality of the predictions. And again, cross entropy, if you search Google or go to Wikipedia, there are formulations how cross entropy is, can be calculated. This is the formula. And there are some details, where is it coming from, if you are interested to learn more about the theories. But again, at the very high level, it just measures how close the probabilities are to the correct token. Now, once we have this loss, it's now time to update the parameters of the LLM. And that's the purpose of the second part, which is optimization. Optimization is just an algorithm that uses the calculated loss value, and then it goes and updates all the parameters of the LLM based on some algorithm. So it updates them such that if we pass the same input to the LLM, it makes more accurate, it predicts more accurate probabilities next time. So that's all it happens. So now if we repeat these two steps multiple times, many times on different samples from the internet data, eventually we would have very good weights for the model, meaning that the model would end up with the weights that if we pass something like Albert Einstein was a German born, and if we look at the probabilities, the probability for the token physicist would be very high. And that's going to be the outcome of the training process. So we continuously sample text from our training data. We pass it to the model. The model output probabilities. We calculate the loss, compare it with the correct next token. And then we apply optimizer to update the parameters of the LLM. And after we do this enough time on the entire internet data, we would end up with a very good next token predictor model, meaning that whatever we pass, like Albert Einstein, we get the probabilities. And those probabilities are basically statistically very accurate, in a sense that if on the internet we see in a lot of places we see Albert Einstein was, the probability of was would be high. So in other words, basically it learns all the dependency and statistics between all different tokens from the internet data. And then it has some implicit knowledge of the world. And that's because if the model can really predict the next token really well, it means that it has some understanding of different domains and different areas and some implicit knowledge. Imagine, for instance, we give the LLM something like, I like machine learning because. The next token and also the future tokens that it would keep generating is probably very relevant to machine learning. So it would probably output some terms that are related to machine learning and to why people like machine learning. And all of these are statistically very close to what is available on the internet. So that's the outcome of the training. Now, remember, these models can be very difficult to train, even though the process is very straightforward, because these LLMs can be very huge in terms of number of parameters. It can be engineering-wise, it can be very difficult and a lot of challenges to make sure that we have the right setup to train these models. For example, I asked ChatGPT that what are the resources needed to train an LLM with 405 billion parameters. And remember, this is what Llama 3, biggest version of Llama 3 has. So what is the memory needed? I misspelled what with why. And then the answer is it requires lots of things. And then here it says why memory is needed. It's first because we need to store the model parameters during training. So all those parameters, 405 billion parameters, needs to be stored in memory. And then during the training, again, there is some algorithms and optimizers needs to keep track of all the intermediate representations and activations and use those to update the weights. So there are a lot of intermediate floating point value numbers that it should store. So because of all of these, and here is a rough estimation, it requires like very large memory, assuming that we use a FP32, meaning that we use 4 bytes to store each weight. We would end up needing around 1.6 terabytes of memory. So definitely it's not possible to train this entire model on a single GPU, because the best GPUs we have might have around hundreds of gigabytes of memory. So it's not practical to really train this big model on a single GPU or on a single machine. And again, in its calculation, it's saying that you need at least 80 to 100 GPUs just to fit the model in memory. And in practice, it requires more. Realistically, it says you use 2,000 GPUs or more. And these numbers are accurate based on what happens in practice. Also here, in terms of storage, we need huge storage as we train the model to just keep saving the checkpoints of checkpointing the new models as we train them. So each time, each checkpoint might exceed 2 to 5 terabytes of storage needed. So all this is basically saying that it can be very challenging to train very large models, very large LLMs. It also requires lots of distributed training and so on. And then let's go to the Llama 3 paper. This is the technical report of Llama 3 published by Meta. And what I want to show here is that if we scroll down, there are this, by the way, this is a great technical report. It's very, very useful to read and learn. I personally learned a lot of things from it. So, but what I want to show here is that, all right, so what I want to show here is that if we scroll down, there is this pre-training stage, which we discussed in the last couple of lectures. And then they're talking about pre-training data. And they manually apply this cleaning and different, basically here they're saying that there are a couple of steps. The first step is the curation and filtering of large scale training corpus. We already discussed about this. Then they talk about model architecture and finally the model training. So pre-training data, they start with something, they apply some data cleaning mechanisms, and here they explain more about safety filtering and text extraction and cleaning from HTML content and so on. And deduplication, we saw all these, why they are important and how it works. And then after the data preparation, they talk about model architecture. So they start with Llama 3 uses a standard dense transformer architecture. So as we mentioned before, most LLMs are all based on decoder-only transformer. And after model architecture is the training. And then here, basically, this part talks about infrastructure, scaling, and efficiency. And if you just read it and go over it, there are a lot of details about storage and compute that is required. And they are, for instance, they are training this model on 16,000 H100 GPUs. And H100 is one of the more powerful GPUs that are available in the market. So they are using 16,000 of those GPUs. And then here also they're talking about how big storage is required and network challenges. And then after that, they talk about all the optimization and techniques that they have to use so they can only fit everything in memory. And they're talking about all different parallelism techniques for model scaling and pipeline parallelism. So what I want to show is that there are, and see this section is very long. So they're doing a lot of tricks and a lot of engineering work just to make training possible on such a big model. So just engineering-wise, I just wanted to say it's difficult, but in theory, it's just these steps. If you look at the code is just calculating the loss using a standard cross-entropy loss function, and then using some standard optimizer to keep updating the model parameters. And then we keep doing this on the entire internet data. And then the outcome would be a model that is really good at predicting the next token based on the statistics of internet data. So I covered all I wanted to cover for the model training. Hello, everyone. In the last lecture, we wrapped up model architecture of LLMs. In this lecture, we want to talk about text generation. Given that we have a trained LLM, how can we use it to generate text? From the last lecture, we learned that if we use the LLM and we pass some input to it, like Albert Einstein, the LLM would produce probabilities for the next token. So it's going to be a vector, and each value would represent a probability of that particular token. Now, for text generation, this is not enough. What we want is we want actually some more text given input text. For example, if we are given Albert Einstein, we want the LLM to generate more text in a meaningful and contextually relevant way. So that's the purpose of step 4, which is text generation. So to do that, text generation is an iterative process. We iteratively generate tokens, and we continue doing that. It's basically a for loop. So to better understand that, let's just walk through a real example. Let's say we pass Albert to an LLM, and then the LLM produces probabilities. Now, in order to go from these probabilities to an actual token, we need some strategy or some algorithm to pick one token from these probabilities. Let's assume that there is some algorithm that does that for us. So it picks Einstein from these probabilities. And then now we have Albert Einstein. So we can pass it to the LLM again. And the LLM produces probabilities for the next token after Albert Einstein. And then the algorithm picks was. And then we can repeat this process. So we can just repeat this process and keep getting new tokens until one of two things happen. So the generation ends when we reach end of sentence a special token. This is a special token that we can use when training the LLM, so that whenever the LLM outputs that, it means that the sentence is complete and we no longer need to generate more tokens. So this is one way that the generation can end. The other way is that the LLM never produces end of sentence token and we reach the maximum desired length. So as soon as one of these two things happen, we can stop this iterative generation and we would end up with a continuation of the initial sentence that we had. So I have a more compact visualization of this thing here, and then it's here. So basically, we start with something, let's say hi, and then the LLM produces probabilities and the algorithm picks the next token, which is how, let's say. And then how comes here. Now the new input is hi, how, goes to the LLM, then we pick R, and we keep doing this. In this case, we reach end of sentence token, meaning that the LLM at some point, which believes that the sentence is completed, it produces end of sentence a special token. So we learned about this iterative generation process. Now, the only thing that we need to answer is the algorithm here. How can we really pick a token given the probability distribution? And that's what we are going to talk next. So basically, there are different algorithms and different strategies. We often call them decoding algorithms or sampling algorithms. And these algorithms specify how to choose a token from a probability distribution. So given that the LLM outputs something like this, which can be interpreted as this probability distribution, the algorithm specifies how to pick the next token from these probabilities. And there are different algorithms for that purpose, and they can be categorized in different ways. So here we have, at a very high level, all the text generation methods or sampling methods. They can be categorized into deterministic and stochastic. Deterministic are the algorithms that there is no randomness in the generation process. So if we repeat the generation using the same input and same LLM, it would always produce the same output. Stochastic algorithms, on the other hand, has some randomness, meaning that using the exact same LLM and exact same input, if we run it twice, run text generation twice, we would get two different continuations or two different generations. And each of them has their pros and cons. So we'll start with deterministic and then we'll switch to a stochastic. Deterministic, there are two popular algorithms. One is greedy search and the other is beam search. Again, we'll briefly talk about this to better understand the evolution of different text generation algorithms. But I want to also point out that in most advanced LLMs, they no longer use any like greedy search or beam search, and they use this top P sampling here, which we will talk about. But it's very good to just have some ideas about how these search algorithms work and what are their limitations. So we'll start with greedy search. Greedy search is basically the simplest form of picking a token from the probability distribution. It, as the name suggests, it greedily picks the highest probability token and then use it as the next token. So it's just very simple. So let's say, for instance, this is the predicted probabilities given the input token how. So the model has predicted these values for different tokens. And in this example, the greedy search simply picks R because it has the highest chance of being the next token. It has 37% chance, and it's more than all other tokens. So another way to visualize this is like a tree. So we start from this input token, which is how. It's passed to the LLM, and then the LLM outputs the probabilities for all different tokens in the vocabulary. For simplicity, we visualize 3 outputs here, but in practice, it's equal to the number of tokens in the vocabulary. So let's say it's 50,000 values. So at this step, the algorithm picks the highest probability token, which is R, with 56%. And now we have how R, it's passed to the LLM. The LLM again produces 50,000 probabilities in the next step. And the greedy algorithm picks U because it has highest probability. And it just keeps repeating this. So at the end, we would end up with a path in this tree. Like how are you doing? So the advantage of greedy search is that it's very simple and efficient. It simply picks the highest probability at each step, and it can be easily implemented. However, there are lots of limitations with greedy search, and it's not really used in practice for text generation in LLMs. The key limitation of greedy search is that it's not really looking ahead. So at each step, it's only picking the highest probability token without looking the probabilities at the future steps. So this may lead to suboptimal generations because there might be better sequence of tokens in other branches. For example, here, even though R has the highest probability, there might be a different branch that if the model, the text generation explores that, it may lead to something with higher probability if we just consider the probability of all the tokens in the sequence. But greedy search does not that. Greedy search just picks the highest probability at each step without looking ahead or considering any other branches. The other key limitation of greedy search, it may lead to repetitive outputs. So what that means is that you would see a sequence of tokens that keeps repeated in the generated text. And the reason for that is because there might be some cases where a sequence of tokens has very high probability and are very common and also commonly appeared on the internet. So the greedy search keeps picking those sequence of tokens because it's just preferred. They have highest probability statistically, and the algorithm just prefers to deterministically just keeps picking them. So that's greedy search. Before we switch to the next algorithm, which is beam search, let's see greedy search in example, in practice. So I have this code here in my Jupyter lab. And then there are some different libraries. Again, the purpose is not to be super familiar with some of these libraries and how they work. But there is this transformers library, which easily gives us access to various pre-trained models and also their tokenizers. So I'm using that to get a model, GPT-2 model, and also its corresponding tokenizer. So let me run this. And then the next thing I want to do is I want to start with some input sentence. For example, I enjoy walking with my cute dog. Now, what needs to happen is that this text first needs to be converted to a sequence of IDs using the tokenizer. So I run the tokenizer on this sentence, and it would give me model inputs. And model inputs is simply a sequence of IDs, or a sequence of IDs corresponding to these tokens. So let me run this. Now, if I print model inputs, we would see a sequence of numbers, 40, 28, 83, and so on. And these are corresponding to these individual subwords or tokens. So now we have model inputs, we have the model, we have everything ready. The next thing is we have to now run text generation using greedy search. And we don't have to implement greedy search from scratch. It's already implemented, and there is this method called generate with some inputs. Again, there are some good documentations to understand what are the inputs, but my purpose here is to only show what it means to run greedy search on some input using GPT-2 model. So here I'm passing all the sequence of IDs, and also I set max new tokens to 40. And what that means is that do not generate more tokens after you generate 40 new tokens. And this is necessary because otherwise the model may generate a lot of tokens and it may never end. So now I run this, and let's see what is the output. So, all right, here, this is the output. It starts with, I enjoy walking with my cute dog. This is my original sentence. And then everything after this is what the greedy search algorithm generated. And it starts with comma. So the continuation is comma, but I'm not sure if I'll ever be able to walk with my dog. I'm not sure if I'll ever be able to walk with my dog. And also here, I'm not sure, which is the continuation is still probably the same token. So the same sequence of tokens. So this is a good example of showing repetition. This sequence of tokens, I'm not sure if I'll ever be able to walk with my dog, is apparently very common sequence of tokens. They have high probability, and the LLM, the GPT-2 model generates very high probabilities for this sequence. And then the greedy search algorithm is deterministic. So each time it just prefers to just pick the same sequence of tokens over and over and over again. So this is greedy search, and this is why it's not ideal to be used in practice for text generation in LLMs. Now let's get back to our lecture and switch to the next algorithm, which is beam search. So the idea behind beam search is to basically fix some of the limitations of greedy search. Remember, greedy search always picks the highest probability token. What beam search does is it keeps track of the top K path in this tree. So for instance, instead of picking the highest probability next token, it would always keep track of the highest probability, like 3 passes with the highest cumulative probability. So for example, if when we pass how to the LLM and we get all those 50,000 probabilities, the beam search would pick top 3 probabilities. For instance, let's say they are come or do with these numbers, and then it just discards everything else. So for the next step, we have 3 paths, 3 possible continuations, or 3 possible sequence of tokens. And they are how come, how are, how do. Now, LLM, again, for each of these, we pass to the LLM, and the LLM generate the next, the probabilities, 50,000 for each of these. And then out of all those 50,000, I think it's going to be overall 150,000, assuming that the output of the LLM has 50,000 numbers. So out of all of them, the beam search comes and look at the cumulative probability. For example, how come animals has 24% here and 36% here. How are you has 31% here, 91% here. And then how do you has also 26% here, 63% here. So these 3 paths are better than all other passes here. So the beam search discards all these possible continuations and only keeps these 3 sequence of tokens, which we have in bold lines. So at second step, we would end up with, again, 3 paths. How come animals, how are you, and how do you. and then it goes to the next step. So it keeps doing that again until a certain number of iterations it reaches. And then finally, it just picks the highest probability path out of the three candidates. So this is beam search. Again, we can think of it as an extension of greedy search by keeping track of top K possibilities at each step. And the advantage of this is that it may sometimes discover better continuations compared to the greedy search. For example, here in this case, it may, at some point, it may decide that how do you is, and the continuations of that has higher probability or is more likely to be a better continuation compared to how are you. So by just keeping track of top K path, it most of the times it outperforms greedy search. So this is beam search. And beam search also has the similar issues of repetitions. A lot of times you may see repetitions when you run it on the LLMs. But overall, you would see more relevant continuations in most examples. So now this is beam search, and then we covered deterministic algorithms. And both of greedy search and beam search are deterministic, meaning that there is no randomness. If we run it multiple times on the same input, we would get the same output. For example, here, if I run this again, I would get the same output. I enjoy walking with my cute dog and the rest of it. Now, the next category of algorithms are stochastic with randomness. And we'll start with multinomial sampling. That's the simplest way of sampling among all these three algorithms. So let's start with that. Multinomial sampling, basically what it does is that instead of picking the highest probability token, it just samples according to their probabilities. So for example, if this is a predicted probabilities by the model, the algorithm at this step would pick R with 37 chance. It would pick is with 21% chance, and so on. So this randomness basically allows it to discover other continuations and not always pick R as the next token. So that's multinomial, but there is a major limitation with multinomial. Because it samples according to their probability distributions, sometimes if they run enough times, it may pick tokens that are less likely or very unlikely. For example, if we run it 100 times, at some point, the next token that it may pick after how might be hard. Now imagine there are some more tokens here that can be they can be grammatically incorrect to come after how. But the multinomial sampling may occasionally pick some of those tokens. So that's why multinomial sampling is not really used in practice in LLMs. And some variations of multinomial sampling is used. And top K and top P are both improvements over multinomial sampling to fix the issue that I just mentioned. So the next thing we talk about is top K sampling. So top K sampling, basically, instead of picking according to the probability distribution of all tokens, it first picks the top K tokens based on their probabilities, and then it samples according to their probability distribution. So this way, it discards the unlikely tokens, and it does not even consider those tokens. For example, in this case, if top K is, let's say K is equal to 3, and K is a hyperparameter, we can define it. But let's assume K is 3, and we want to run top 3 sampling from this probability distribution. First, we keep the first 3 highest probability tokens, which are R, is, do. We discard everything else. And then out of these 3, now we sample 1 token. So this is where the randomness is introduced. So top K is clearly better than multinomial sampling because it simply discards what is very unlikely to come next and only keep likely words and then sample from those. So this is top P, but top K But top K has also one limitation that we'll talk about, and that's what top P sampling is trying to fix. So let's go here. So imagine these two different probability distributions. In this example, we have probability of next token for thanks A. And then these are the probabilities. You can see thanks A lot. Lot has the highest probability, 89%. And then everything else is very low. Now, if we run top K algorithm on this, and K is, let's say, equal to 3, it means that we are going to keep the first 3 tokens and consider all these 3 lot, much, high as a candidate for the next token. However, the model is somewhat confident that this is the token. These are very unlikely to come next. But top K, since K is fixed, would always consider top 3 tokens. Now imagine this probability distribution, which is the probability of tokens coming after how. For this model, top K, again, it would consider top 3, let's say. It would consider the first 3 tokens, or is due, and it would ignore the rest. However, in this example, according to the probabilities, the model is also confident about some other tokens. So it's more uniform, the predicted probability. So there are more tokens that can be good candidates to come next, to come after how. So all these explanations, what it means is that top K, because K is fixed, is not a good, is not an ideal algorithm. Because regardless of the shape of this probability distribution, it would always consider the top K tokens. When the model is very confident about, let's say, the next token, it would still consider top K. And when the model is not too confident and there is a huge possibility of candidates, the model would still pick top K. And that's what top P sampling is trying to address. So what top P does is basically it does not fix K. What it does is that it picks the top K tokens that their cumulative probability exceeds value P. Now, this P is a hyperparameter that we can provide and we can pass to this, we can specify in this sampling algorithm. For example, we can say top P equal to 90%. Or in this example, we have 88%. P is equal to 88. When it's 88, it means that pick the first few tokens such that their cumulative probabilities exceed 88%. And in this example, because the model is relatively confident about the next token lot and it has already 89%, it exceeds our threshold, and top P sampling would only consider this. In this example, since the model is less confident and there are more possibilities, the model would pick these 4 tokens because the first one is 31% and it's not still exceeding 88% threshold. The next one is 29%, so their sum is 60, and still it's below 88. So at this point, the sum of these tokens exceeds 88. And then the model discards the rest of the tokens and sample from this. So basically, top P is just an improvement over top K with a more dynamic K. It dynamically changes K, and it basically dynamically decides on K based on the cumulative probabilities. And top P is what is commonly used in practice in LLMs to generate text. Let's go back to my Jupyter notebook and see if I run top P on the same input, what's going to be the output. So again, I'm going to use the same I enjoy walking with my cute dog. And then I have top P sampling here. Again, model.generate works with that. We just need to specify do sample true and provide the top P value. In this case, I'm saying 92, meaning that I'm saying that use the tokens that their cumulative probability are 92, and then discard the rest of the tokens at each step. Now, if I run this, I'll get this output. I enjoy walking with my cute dog. This is the original sentence. And now the rest is comma, and then says RM, whatever, 65, who is on a leash at home. So again, it's not the best continuations, and that's because GPT-2 is not the best model out there. If we switch to some better models, we would see a lot better continuations. But at least we are not suffering from like repetitions or things like that. And also there is some randomness, meaning that if I rerun this, I would see a different continuations. Let me rerun. Okay, now I'm clearly seeing something different. I enjoy walking with my cute dog. I don't know what that is. And then it's saying, I love walking with my baby dog and having an empty apartment without dogs and other conveniences. Again, these continuations are not the best, but it's not because our sampling algorithm is bad. It's because GPT-2 is not too good. If we simply switch GPT-2 with something more powerful, like GPT-3 or even more powerful models, we would see a lot better continuations. And in future lectures, we would do that to see how different the output can be. So this is top P sampling, and there are some great like tutorials about these algorithms and the strategies and how different they are, what is going to be the output, the details of the arguments to use this generate and everything. So it's an interesting read. I've included the links in the lecture. And also here is basically another very interesting tutorial, how to generate text. Both of them are published by Hugging Face. So it basically starts with the introduction, and then it starts from greedy search, and it just goes and switches to more advanced algorithms. And then I think at the end, it talks about top K and top P and some examples. So it's an interesting read, but basically it just explains what we already discussed in the lecture. So the next thing I want to share is that top P has these P hyperparameter, and there are also some other hyperparameters that we can specify or introduce in our sampling algorithm. For example, we can always we can have a hyperparameter to adjust the raw probabilities. So for example, when the model output these probabilities, we can just make it a little bit smoother, or we can make it sharper. So these are some of the things that are basically, there is no best or optimal values. It just depends on the task and depends on our model, what are the best values for the P or some other hyperparameters. So you would see some of those values when you try to call LLMs. For instance, here you saw that how we specify top P, and there are potentially more arguments here that we can specify. And I'm not going to go too deep into that. Just one thing I wanted to show here is that, again, as I mentioned, it's very empirical. We have to try an experiment based on the model and based on the task. And also for different tasks, there might be different p-values that are optimal. For example, this is just a very empirical temperature and top P ranges for different tasks. Temperature, again, it refers to a hyperparameter that smooth the raw probabilities. So we can use it to make the raw probabilities sharper or more uniform. So for example, for code generation, it's been seen that top P of 0.1 is a good number. And what that means is that basically we are saying the algorithm to only consider very few tokens, not many tokens as candidates. And that's because code generation is tricky. It's important. We don't want to really, we don't care about novelty. What we want is that we pick the tokens in the code that are in syntax-wise, they are correct and they can be run. So we don't really want to consider all those uncertain tokens that the model predicted. However, in more like creative tasks, like creative writing, we want to increase P because now we want more novel continuations as well. So we always want the text generation algorithm to consider less likely continuations that might be more interesting or exciting. So that's all I wanted to cover for text generation. And in the next lecture, we'll switch to post-training. Hey, we're finally going to focus on the post-training stage. In the previous lectures, we discussed and wrapped up pre-training, and we saw that after the pre-training stage, we'll get a base model that is really good at predicting the next token. And then we can run text generation to continue text, given some input sentence. Now, that base model is not useful because it's going to just continue whatever input sentence is given to it. And it's not necessarily going to answer your questions. Now, the purpose of post-training is to adapt that base model so that it answers questions and also be more helpful and safe. And post-training has two steps: supervised fine-tuning, or SFT, and reinforcement learning. And we are going to talk about both of these in this lecture. Before talking about SFT, I want to go back to our Jupyter notebook and see what we mean by when we say the pre-trained model is good at continuing sentences and not answering questions. So this is, again, the same library, transformers. I'm going to pull GPT-2 model and its tokenizer. All right, and we'll use the same sentence: I enjoy walking with my cute dog, and then use top P sampling with some optimal parameters. And then we'll run it to see what the output is. And remember, top P is the best sampling method that is available and mostly used in LLMs these days. So the output is: I enjoy walking with my cute dog. My wife and my friend, they always have me covered with a blanket, and so on. So the sentence is basically just a continuation of what we provided as the input. Now, also remember that pre-training stage, we previously said that it's the very expensive stage, and it's most important part because it learns from internet data. So this base model, even though it's just a next token predictor or just continues the inputs, it is a still very powerful model. It's basically, it has all the implicit knowledge that it could have seen on the internet. So what that means is that if we changed it to, for instance, I like machine learning, because it would continue this, but now it would continue and use words and terminologies that are very relevant to machine learning and why we like it and so on. So what that means is that it has some implicit knowledge about machine learning, what are typical words, how they follow each other, and so on, which can make this model very powerful. So it says, I like machine learning because it's easier to understand and you can use it to predict what people are going to say. It's not like you can do that in an e-learning system. So again, it's not the best continuation, and that's because the model is not too capable. It's just GPT-2. But just the fact that it's using relevant, like contextually reasonable words, for example, it uses predict or system or e-learning, those are all things around machine learning. Now, if I change this to a more complex input sentence, let's say in quantum computing, let's see what it answers. In quantum computing, we can take an equation and generate an equation with the result that we can divide by the number of different elements in the equation. Again, it's not a useful continuation, but still it's using some kind of relevant terminologies or keywords. So again, all I wanted to show here is that the base model is capable. It has implicit knowledge of the word because it has seen internet data and it has learned from it. It has seen lots of different domains and areas, and it knows how different words and terminologies occur or co-occur after each other in different domains. But the model is not really good at answering questions. For example, if I change this to something like how is the weather? It's going to probably just, how is the weather? Weather is one of the most common problems for people who are tired and stressed. So it's not really answering my questions just because it's the base model. Now, we also discussed that more capable models are bigger. They have more parameters. They could have billions of parameters. For instance, GPT-3 had 175 billion parameters. And then more recent models like Llama, the base model has 405 billion parameters. So it's not even practical to load it on a single machine. And I'm not able to load that here locally and show you how it responds. But there are different services, online services that we can use to load those models and interact with them. And again, there are many examples. One example is hyperbolic. And I just want to show that if I switch GPT-2 to something more capable and bigger, how the response would be different. So here we can select a model. I have selected Llama 3.1405B base, and the name is clear what it means. Llama is basically Meta's LLM. 3.1 is the version, one of their recent models. 405B is showing their number of parameters. It has 400 billion parameters. And basis means that this model is the outcome of the pre-training stage. So this is the base model. It just continues the sentences. It's not going to answer questions. Now, this is also the max tokens. I'm going to reduce this to 60. And then we'll keep these default. These are top P, temperature. These are the hyperparameters to control the text generation process. And what I'm going to enter here, so in the notebook, we saw that for something like I like machine learning, because the output was not really too useful, because it's easy to understand and I don't have to worry about that, he says. And this is just because the model is not good enough. Now here, if I enter the exact same prompt, I like machine learning, because let's see what Llama would respond. I like machine learning because it's a set of tools that can be applied to a variety of problems. You can use machine learning to predict the price of a house or the probability that someone will click on an ad. You can also use it to identify faces and so on. So again, as you can see, now the continuation is a lot more meaningful and also relevant to the input sentence. So that's why bigger models or base models basically has an implicit knowledge about the word, because they're really good at understanding text and continuing them in a relevant way. So now if I also change it in the other example in quantum computing, let's see how it responds. We often want to construct a circuit to perform a particular operation. One way to do this is to design a circuit directly. Again, I'm not an expert in quantum computing, but when I read this, it makes sense. So again, the model seems to be doing well. And then the last example is I want to now enter a question. For example, I want to see, I want to write what is the best way to learn machine learning? Originally appeared on Quora, the knowledge sharing network, where again, it's just continuing it. It's not really answering my questions. So now back to the lecture. The focus of post-training, as we mentioned, is that to adapt this base model, which is very powerful and has implicit knowledge, to adapt it so it answers questions instead of continuing them. And we'll start with the first step, which is supervised fine-tuning. So again, we have supervised fine-tuning as the first step. It's also sometimes it's called instruction fine-tuning, because we are fine-tuning the base model so it follows instructions. And the goal of this stage is to adapt the model from a completion model to following instructions. So for example, if from the base model we ask a question like, I want to learn ML, what should I do? The model may continue with things like with more questions maybe, something like, is it even easy? I'm not so confident, and so on. But after this SFT stage, we'll get the SFT model. And then if we ask the same question, it would actually answer the question. It would say something like, take Andrew Ng's course on Coursera. Now, just out of curiosity, let me ask the exact same question from Llama 3 and see if it really adds more question to it or just answers it. I don't know what happened. Let me try again. All right, maybe it's down. We can try later, but I'm sure it's going to answer. It's going to continue it with more maybe questions, or it's not for sure going to answer it. So back here, in order to complete this SFT, we'll follow the same process as we discussed in the pre-training stage. First, we will prepare data, and then we'll train it. So let's start with the data preparation. The data preparation is basically, the goal here is that instead of having the random text sampled from internet, we'll have data in a particular format, because now we want to show to the model examples of prompt and responses, or questions and responses. So basically, we have to curate a data set that has this format. For example, it has prompt with some special token, and then it has the prompt here, give 3 tips for staying healthy, and then special token for response, and the actual response with 3 tips. Now, if we have a lot of examples in this format, then we will use it to continue training the base model on this data. So this data is also called demonstration data, because basically we are demonstrating to the model that learn from this format and follow this format. Now, there are different data sets and there are different examples of this data set, but the main thing is that this data has to be curated manually. In practice, it's often usual to hire some experts or annotators and then ask them to create these pairs. So one example, for instance, is alpaca dataset. Just to get a sense of how the data look like, I have the link open here, and this is the data. It's basically very similar to the pre-training data, but now the difference is that it has instruction column and output column. So these are things like give 3 tips for staying healthy and the output. And then there are more examples like how can we reduce air pollution, describe a time when you had to make a difficult decision. So again, it's basically a bunch of questions and responses. Now, this is Alpaca. It's available online. It's open source. But there are also some other data sets. For example, OpenAI has Instruct GPT dataset. So what happened was that they trained GPT-2 and then later GPT-3, but both of these models were only pre-trained. So they were not doing any post-training on those models. And then later, they published a paper, this paper, training language models to follow instructions with human feedback. And what they did was they continued training GPT-3 model and running post-training. So basically, they ran SFT and then reinforcement learning on the GPT-3. And then the outcome of that model, the outcome of this process was basically the fine-tune model. And that model, they called it, GPT 3.5 or Instruct GPT. And also, this paper was released in March 22. And then ChatGPT was released and launched a few months later. So I believe that probably this model was used and then probably some additional optimizations was happening on top of that to use as their initial model on ChatGPT UI. So again, this paper, it's an interesting read. And what I want to focus on is their data set. So they hire experts and then they manually create those pairs of prompts and responses. And then they call it Instruct GPT dataset. And then they do not release this dataset, and it's not open source, but it has around 14,500 examples of such pairs. And again, there are a lot other examples that are open source now, like Alpaca, Dolly, Flan by Google. And all of these instruction or demonstration data usually ranges between like tens of thousands or maybe hundreds of thousands of examples. So it's a lot smaller than the pre-training data, which is the entire internet. However, the quality is very high. The pre-training data, it's just all the data on the internet, and many of those, even after we clean them, might still be noisy and not too helpful. But this data, since it's carefully curated by experts, it's usually very high quality. And again, nowadays, if you search Hugging Face for instruction tuning datasets, there are lots of examples. And some of these are for different purposes. For example, this has name No Robots. And I'm sure some of these are more focused on math and mathematics, math instruct, and so on. So there are lots of examples. Some of these can be used to just run SFT and experiment and see how the model learns from these examples. So this is data preparation. Basically, it's going to be thousands of these examples, prompt and response. Now, after this data set is prepared, the next step is running training. Training is very simple because it's identical to what we saw in the pre-training. We don't have to change a single line of the algorithm and anything. So all we need to do is just replace the pre-training data with this SFT data or demonstration data. And then we continue training the base model. And then after enough iterations, we would get the SFT model. So everything is identical to the pre-training stage. And that means that we'll use the same loss function. We'll use the same optimization. And then we'll just sample from the demonstration data with things like what is the capital of France. And then we ask the model to predict the next tokens. So this way, basically, the model would learn from the SFT data to answer questions. So that's training. It's very straightforward. We don't have to change a single line. And then after training, the outcome of SFT stage is the SFT model. And the SFT model would now answer questions. So if you ask, I want to learn ML, what should I do? It would really answer something like take Andrew Ng's course on Coursera. So we talked about SFT stage. Now, this model is not still ready to be deployed. And we'll talk in the next lecture why this model is not ready and why we have to have another stage. And that's called reinforcement learning to make this model ready for deployment. Hey, we talked about the SFT stage. And in this lecture, we'll switch to the second step of post-training, which is reinforcement learning. Before we talk about the actual algorithm, let's understand what is the problem. The problem is that after the SFT stage, we get this LLM, and then this LLM is good at answering questions, meaning that if we ask a question like, I want to learn ML, what should I do? It's going to output something that basically answers to your question. For example, it would say, take Andrew Ng's course on Coursera. Now, this response is contextually relevant, it's grammatically correct, and it's answering my question. But now let's compare this with a different output. For example, something like start with a solid foundation in Python, linear algebra, probability, and statistics. Then take a beginner-friendly ML course like Andrew Ng's on Coursera. Practice by building a small projects and exploring real data sets. Now, both of these answers are correct and contextually relevant, but this answer is clearly much, much better than this answer. It is more detailed, it's also more helpful, and it's giving me some starting points. The focus of reinforcement learning to go from this kind of output to more detailed, accurate, correct, safer outputs. And that's what we want to happen in reinforcement learning stage. I have another example here to better understand. When we have a prompt like, what are some effective ways to reduce my stress? The LLM may have different options to respond to it. For example, response 1 can be go skydiving for an adrenaline rush. Second response is exercise regularly and maintain a healthy diet. Third response is shame on you, try meditation. And fourth response can be ignore your problems and hope they go away. Now, again, all these are possible from SFT output because they are actually answering questions and they're not too off in terms of their context. For example, when it says ignore your problems and hope they go away, it's actually answering to these questions. It's not answering to a different question. But the response is really not helpful because by ignoring your problems, it's not going to help you. Response 3 is a mix. It's giving good advice like try meditation, but it's not polite. It's not a safe response. And response 1 can be not accurate, but still it's responding to the prompt. And this one is the best one. So the goal of reinforcement learning is to somehow adapt the SFT model and get a final model that is more likely to produce responses like this. and less responses like these three. So now let's start about learning the technicals. So reinforcement learning goal is to generate responses that are preferred by humans. So which responses are preferred by humans? Typically the ones that are correct, accurate, safe, helpful, polite, and so on. So after we complete the RL stage, we go from this SFT model to this final model. And this final model is basically what eventually we would use and deploy as a chatbot. But how do we do that? How does this reinforcement learning happens? It's basically the training algorithm at a very high level, just to get an intuition, is basically a practicing algorithm. We allow the SFT model to practice. So what practice means is that we give it some inputs and we ask the SFT model to produce different responses. So each of these arrows here is basically showing one response to this prompt, what is 2 plus 2 by SFT model. So here we have 1, 2, 3, 4, 5, 6, 7 responses. And then based on these responses, we say, hey, this response and this response was better. And these 5 responses that are in red are not good. So then the training algorithm goes back to the SFT model, updates its parameters, so that next time when we pass a prompt like this, it would be more likely to produce responses that are green, that are more similar to these green responses. So that's the high-level idea. The model practices. It generates responses for the same prompt, and then we somehow we share with the model that which responses are better, which responses are worse, and then the model tries to reinforce itself, basically reinforces such that it generates more responses similar to the ones that we liked. So how does this happen? Basically, the main question is how can we really, once the model generates these variations of responses, how do we determine which responses are better than others? To answer this question, we can split all the tasks in the world into 2 groups, verifiable and unverifiable. Verifiable tasks are the ones that we can easily verify the response if it's correct or not. For example, if we think of math problems, and when we have something like this, what is 2 plus 2? It's a math problem. We know that the answer is 4. Answer 4 is correct. And then we can just look at all these responses and look at their final answer at the very end and see which of those are 4. If they are 4, they are green. They are good. We want more answers similar to those. And if they are anything but not 4, they are wrong. It doesn't matter if the logic or the reasoning is correct. It's just we don't like it. And coding is also another example of verifiable, because we can easily verify code if we can run it or if it produces the output that we expect or not. But there are also unverifiable tasks. For example, if you think of writing or brainstorming, it's not really easy to identify or say if output is correct or not. It's very subjective, and it's also relative. So, for example, for brainstorming, if the input is, help me choose a good name for my startup, there might be various responses, and then some of them are better than others. But there is no really easy way to verify if they are correct or not. And those are unverifiable. And these 2 groups of problems are handled differently in the reinforcement learning stage. We'll first start with verifiable. We understand how training works in verifiable problems, and then we'll switch to unverifiable problems. So again, verifiable is easier because we can have some logic here, some software, some Python code to look at the responses and then basically check if their final answer is similar to what we expected or not. So basically all we need is a data set. And for things like what is 2 plus 2, if we know the answer is 4, we can just let the SFT model generate various responses, apply this code or logic to all these responses, and then automatically label them as correct versus incorrect. And then once we have this, the second step is now the actual training or the updating the model. So during the updating, we use some algorithm, some reinforcement learning algorithm. There are various algorithms like PPO, more recent GRPO, and so on. And then this RL algorithm is basically given the prompt as well as the labels, which ones are correct, which ones are not. And then the PPO is responsible for updating the SFT model parameters so that it reinforces correct answers. So there are lots of wonderful resources for learning in detail about RL and PPO and how they differ. But at the high level, all they do is they're responsible for updating the parameters of the model in a way that reinforces the better answers. And then after we update the model, again, this is the final model. It's already a model that is reinforced to produce correct answers. So when we ask a question like, what is 2 plus 2? It's more likely that generates something that leads to 4. So this is verifiable tasks. And at the core of it is this PPO algorithm. And then the verification here happens automatically and easily because the task is verifiable. Now let's switch to unverifiable tasks. So now in unverifiable tasks, the challenge is we no longer can automatically label these responses. We really don't know which ones are better than others. For a prompt like how should I learn ML, it's really not easy to say, if they're very close, it's not really easy to say which ones are preferred. So because of that, we need a way to first score these responses. We need to score each response. And then after we have those scores, then we can follow the same process as the verifiable. We can just train a machine learning model and basically use reinforcement learning to continue the SFT model based on those scores. So now the next thing that we would learn is how are we going to score these responses? And for that, we have to train a separate model. So, and this is called RLHF, reinforcement learning from human feedback. Basically, we use human feedback to train a model that can score these responses. And then once we have that separate model, we'll use it to automatically score responses. And then we can use reinforcement learning to update SFT model. So basically, there are 2 steps in RLHF. Training a reward model using human feedbacks, and then optimizing the model, the SFT model, with the reinforcement learning algorithm using this trained model. So this is a step 1, training a reward model. The data preparation part is basically we initially collect some prompts. These are some initial prompts, like things like what is the capital of France, name a famous physicist, and so on. We use the SFT model to generate multiple responses for each prompt. For example, for the first prompt, which is what is the capital of France, we have response 1 can be Paris, response 2 can be it's in Europe, and response 3 is it's Eiffel Tower. Now, then we need actual humans. We need to hire annotators to rank these responses. So here, basically, actual humans look at all these responses and rank them. For example, in the first example, Paris is obviously better than it's in Europe because it's more accurate. And then it's in Europe is better than Eiffel Tower. So this is the ranking. And then after we have all these rankings from the prompts, we can finally generate our training data. And this is how training data will look like. What it would have, each example would have a prompt, which is the prompt here. What is the capital of France? And then we'll have winning response and losing response. For example, based on these rankings, we can say Paris is better than it's in Europe. So one example, we can form it by something like this. Winning response is Paris. Losing response is that it's in Europe. And then we can also construct more examples based on these rankings. We can go and say, hey, what is 2 plus 2? For winning response, math is hard. Losing response, just because from the annotators, we know that this response is ranked lower than this response. So this is how we get the training data to train a reward model. Again, in the reward modeling stage, the only purpose is to train a model that can reward answers, that can basically score answers. So after we have this data, the second part is training the reward model. And this is a very typical problem in machine learning. Basically, we have a model that takes prompt and response and score them. So this is the input and output of the reward model. We have one prompt and one response, and the model outputs a score. Now, in order to train this using these training data examples, prompt, winning, losing response, this is how we would train it. We pass the prompt like what is 2 plus 2 and winning response to this model. We get some score. We also pass the prompt and the losing response. We get another score. And then we apply some common losses, such as margin ranking loss. And what this loss does is basically tries to maximize the difference between these scores. So what it does is it tries to increase the score of winning response, and then it tries to minimize or lower the score of losing response so that their difference be maximized. Basically, this is the objective. So that's it. It simply uses this a loss function like margin ranking loss for this purpose. And then after we train this model on our training data, on this data, eventually we would have a model that when we pass a prompt and response, it would predict the score. And this score would align with humans' preferences or feedbacks, which we obtained here. So now this reward model will be a proxy for humans. Instead of humans going and actually ranking these responses, the reward model would now score them. So we talked about the first step of RLHF, training a reward model. The second step is almost identical with what we saw in the verifiable tasks here. It's very similar to this. The only difference is that now we don't have an automatically verifiable component, which is easy to implement. Instead of this, we have now a reward model. So let's go to the optimizing the model with RL stage. Again, very same process. We use some reinforcement learning algorithm to update SFT model's parameters using the scores. And the scores are obtained by the reward model. So for a prompt like how should I learn ML, we pass to SFT model, we get multiple responses. The reward model scores each response. And these scores are the hope is that these scores would align with what humans would have scored because the reward model is trained on human preferences. And then the PPO algorithm would take these scores and the prompt, and it basically updates the parameters of SFT model. So next time it generates responses with higher scores. So it reinforces responses like this and this with higher score. So that's the second stage. And then after we apply this reinforcement learning, we would end up with a model that produces answers that are more aligned with humans. And that means that they are more correct, they are more detailed and useful and safe. So for a question with like, I want to learn machine learning, what should I do? We saw this example. They would output something like a start with solid foundation in Python and so on. So this is post-training, and we talked about both the stages of post-training. We talked about, let me go here. So we talked about both SFT stage, which is responsible for just adapting the format of the output to answer questions instead of continuing it. And then we apply reinforcement learning so the model practices to produce more accurate, correct responses. And then during the reinforcement learning, there are two types of tasks, verifiable and unverifiable. Verifiable tasks are the ones that we can easily learn them. That we can easily verify them, such as math problems and coding, and unverifiable are the ones that are difficult to verify. For verifiable, we can just simply have a component to rate score these responses, and then we use reinforcement learning to update parameters. For unverifiable, we would train a new model called reward modeling to score these responses automatically. And then once we have that, we can then apply reinforcement learning to go from the SFT model to the final model. So that's it. That's all I wanted to cover for post-training. And one last thing before we wrap up post-training is showing this a real example. In the last lecture, we saw that how a base model would simply continue. Let me rerun again to see if it's going to work now. I want to learn ML. What should I do? All right. So again, the base model, just keep asking more questions. What are the resources I should follow, and so on. Now, what I'm going to do is I'm going to switch to a model that is not a base model. It's a post-trained model. So here we can choose one of these models. I'll see if I can find the Llama 3.1. All right. I'll choose Llama 3.1, 405 billion. So it's the exact same model, but not the base model, the post-trained model. And I'll ask the exact same question here. So the UI is a little bit different. I'll ask my question here and then send it. And then I'll keep max tokens to 512 so it produces more tokens. And then let me send this. All right, now this is the response, and it says learning machine learning is an exciting journey. Here is a step-by-step guide to help you get started. A step one, and math, programming. A step two, it also takes care of the formatting, like showing this like listed itemized sentences, and some of the words are bold. So basically, it's just answering my question in a very detailed and helpful way. And this is what happens when we apply post-training to a base model. It becomes a really useful model. So that's it now. Now I guess I can wrap up the post-training. Hey, let's start by reviewing a summary of LLM training stages, and then we'll focus on how to evaluate a trained LLM. So these four stages are basically summarizing everything we discussed over the last couple of lectures. There is the pre-training stage. It's trained on internet data, typically trillions of tokens. They're low quality, large quantity. And then they require a lot of computes. They need thousands of GPUs and months of training. And then it's the language modeling algorithm and objective is just next token prediction. So we train them to predict the next token. And then the outcome is the base model. And we saw some examples like Llama base and GPT-2 and 3. And then the second stage is supervised fine-tuning, which is part of the post-training. In this stage, we build and curate our demonstration data on pairs of prompt responses. They typically range in the range of 10 to tens or hundreds of thousands of pairs. And then they're low quantity, high quality. And this stage requires only hundreds of GPUs or even less and days of training. And the ML objective is the same. We still have the same model, same training algorithm to predict the next token. And then the model is initialized from the base model, meaning that we continue training the base model, and then the outcome becomes SFT model. And then the next part is creating a reward model if the tasks are not verifiable. And then reward modeling, we need comparison data. So we hire annotators to rank possible responses generated by this SFT model. And then this stage also requires hundreds of GPUs or less and days of training. And then here, the goal is to train a reward model that can predict the scores. So the output is just a score. This is the ML objective. And then once we have the reward model, we'll start the final reinforcement learning stage. It's initialized from this SFT model here, and it relies on reward model to score rewards. And then for reinforcement learning, we start with tens or thousands of or hundreds of thousands of prompts. We use smaller number of GPUs and days of training. And then we use a reinforcement learning algorithm to so the model practices to generate responses that are scored higher by the reward model. And then the outcome of this stage is the final model, which is typically used to deploy and serve users as a chatbot. So this is the summary of training stages. And after we complete all these stages, we will end up with the final model. And there are different companies having different models. And if you see here, again, there are lots of models like the ones from DeepSeek and Qwen, and there are basically a lot, and Llama, and there are a lot more examples, small, large, and so on. So the question is, how should we evaluate them? How can we determine which models are better and which are worse? And this is what we are going to talk about in LLM evaluation. So there are two parts in the evaluation. The first part is offline evaluation, and then the second part is online evaluation. In offline evaluation, we evaluate the model in an offline environment on some evaluation data. And then we measure the performance, and then we compare different LLMs. In online evaluation, we have the LLMs already deployed in a production environment, and then we use different ways to compare them while they are in production and serving users. So we'll start with offline evaluation, and there are different ways for offline evaluation. We'll start with traditional way of evaluating, and then task-specific and human evaluation. And then for online evaluation, we'll talk about human feedback and crowdsourcing platforms. So the first one is traditional evaluation. What traditional means here is we use some traditional metrics to evaluate LLMs. And one common metrics to evaluate LLMs and in general a text generation model is perplexity. And it's basically a metric that measures how accurately the model predicts an exact sequence of tokens present in the text data, often in the evaluation data. So there is a formula, and then you can look on Wikipedia to see the details of the formula. But at the very high level and intuitively, what this formula is doing is we'll have some sequence of data, let's say our evaluation data, for example, how are you doing? And then we use the model to see how likely is it to produce this exact how are you doing sequence. So we start with how, we get the probability. Then we pass how are, we get the probability of you. And then we have basically, in practice, like theoretically, we have to multiply them, or we can basically take the log of these values and then sum them. And then this would give us a number representing how likely the model is to produce this exact sequence of how are you doing. And this way, basically, we measure how good the model remembers evaluation data or can exactly reproduce evaluation data. And then this way, we can compare different models, and the model or the LLM that is better at producing or reproducing the evaluation data is better. However, this method, this traditional way of evaluating LLMs is no longer too helpful or meaningful, because this metric is not really telling us much. What it says is that the model can reproduce a certain sequence of tokens, but that's not what humans want really in practice. What we want is a model that can really answer our question, or it's correct, or it's useful. So that brings us to the second way of evaluating LLMs, which is task-specific evaluations. So the purpose of this kind of evaluation is to assess the performance of LLM across diverse tasks that we really care about. For example, mathematics, code generation, common sense reasoning, word knowledge, and so on. So these are some of the key areas that we want to evaluate the model and see how the model performs. So we'll just briefly review some of these. And there are great benchmarks, meaning that benchmarks are basically just a data set with certain examples in that particular domain. And then we can use those and run them on, pass the prompts to the LLM and see if the LLM response is similar to the correct answer. For example, common sense is just common sense questions. If the model can answer those questions or not. This is one real example. The trophy doesn't fit in the brown suitcase because it's too large. What is too large? The trophy, A, B, the suitcase. This is the prompt. This goes into the LLM. And then the correct answer from this data set, from this example, is the trophy. So we pass this to the LLM and we see if the LLM really generates the trophy, or it generates the suitcase, or anything else, like any random outputs. And then this way, we can compare different LLMs and see how well they are doing in, let's say, common sense reasoning. And there are a bunch of benchmarks for each of these domains. We have listed 3 benchmarks here. And then for word knowledge, for example, who wrote this, who wrote that, and this is the correct answer, and these are the benchmarks, and we can use LLMs and evaluate them on their word knowledge capability. And then we have mathematical reasoning. For example, if a train travels 60 miles per hour for 3 hours, how far does it travel? And then we see if the model can really answer correctly or not. And then we have also code generation, something like write a Python function to check if a number is prime. And then this is some possible correct answer. And then the model also generates an answer. And then we can check and see if the outputs are correct or not. And these are some benchmarks for code generation. So this way of evaluating LLMs is very common because we really care about these numbers and we want to know how good different models are compared in different domains. So this is a common way of evaluating LLMs. And then the last part, which we had here, is human evaluation. Basically, in this type of evaluation, we just ask higher experts and expert humans. And then we ask them to ask challenging questions from the LLM and see if their answers are correct or not. So this can be tricky. In one sense, it's good because humans are more capable of evaluating and understanding the responses and verifying them. But also it can be tricky because humans can be biased, and a lot of times, depending on who is evaluating an LLM in which domain, the responses or their evaluations might be slightly biased and also subjective. But this is also another way to evaluate LLMs. And then we'll switch to the online evaluation. In online evaluation, we have two ways of doing it. One is human feedback and another is crowdsourcing platforms. So human feedback is simply just when the model in the UI, in let's say ChatGPT UI, it responds, it asks the user to rate it with a thumbs up or a thumbs down. And this way, the team behind ChatGPT can get a feedback from real users, whether they're happy with the answers or not. And this would give them a signal whether how good the model is doing compared to previous models. And this signal can be also used for other purposes, like for further fine-tuning or doing reinforcement learning, because these feedbacks are coming from real humans, so they can be valuable. But they can also, they serve as an evaluation purpose as well. And then the final part of online evaluation is crowdsourcing. So there are different websites that they use crowdsourcing to rank and rate LLMs. And one common example is this LM Arena. And it's initially developed by Berkeley graduates. And if I search Google, it says that LM Arena is a public web-based platform that evaluates LLMs through anonymous crowdsourced pairwise comparisons. Users enter prompts for two anonymous models to respond to, and then vote on the model that gave the better response, in which the model's identities are revealed. So basically, just ask the real humans. It shows them two different responses from two different models, and then the users can vote. And then it uses those votings to rank LLMs. And then this is their website. So there are different tabs here. I selected text. And text means basically the models for like LLMs, the models that are ranked. Basically the models that are ranked for their text generation capability. And this is the ranking as of today. For example, the first rank is Gemini 2.5 Pro, developed by Google. And these are the number of votes, and this is the score, so we can see the gap between different models. And then this is the license. Some of these are open source, some are closed. The second rank is O3, and then we have ChatGPT 4.0, 4.5, Claude model, Claude 4, Opus 4, and so on. And this is DeepSeek, which has this MIT license, which basically is open source and we can use it. And it's also open weight, so the weights are available to be used. And you can see there are lots of different models and they're ranked, and this table keeps changing. And these companies keep releasing new models, and just usually newer models are better, so they ranked higher. And again, it keeps changing and changing. So I think it has like lots of LLMs now. Yeah, 211 LLMs are included in this table, and then Llama 13 billion is 209. And these are relatively older models, and that's why they are lower on this list. So yeah, so that's it. That's the crowdsourcing platform. So these are all different ways that we can evaluate LLMs, and they are used in practice to see if a newly trained LLM is better than the previous ones or not. Hello again. This is finally the last lecture of week 1 of LLM Foundations. So we learned everything about the foundations of LLMs, how the data preparation looks like, how the model architecture is, model training, both the stages, pre-training and post-training, and also evaluation. One last topic that we want to cover in this lecture is the overall system design and what is the holistic view of like chatbot systems. So as you can see here, trained LLM, this is basically the post-trained model that we finished training is here. And then, it's just very small part of the entire system. And then there are a lot of other components that are necessary and used in practice to power a service like ChatGPT. And this is simplified visualization. In practice, there might be even more components handling different things. But this would give a good overview of what are different things that are important and needs to happen aside from the actual trained LLM. So let's just walk over them one by one and understand what are their purposes. So when we have the text prompt coming from the user, the first component usually we have is some guardrails for input guardrails. And we can also call them safety filtering. So all this component does is it ensures that our text prompt, the text prompt that was provided by the user, is a safe prompt, meaning that it's a safe request or safe question. For example, if the user requests something that is violent or could be harmful, at this step, this component would identify it and just not answering it. So basically, if the result of the safety filtering is that it's not safe, if it determines it's not safe, then it would use some other smaller models to generate some rejection response. So this generated response would be shown to the user. And this is something like, hey, sorry, we cannot assist you with that, or things like that we've seen on various platforms. Now, if this component identifies that the text prompt is safe to process and answer, the second part is usually a prompt enhancer. And what this component does, most of the times it's a machine learning based model. And what it does is it improves the text. So a lot of times in the input text, there is ambiguity. There can be some misspellings or grammar issues and all those kind of different problems in the initial text prompt. So this component is responsible to fix all of them. It's responsible to make sure punctuations are well and they are there in the prompt. There is no misspelling. There is no typos. If there are typos, they get fixed. And also if there are ambiguity or the grammar is not correct, they all get fixed. And it can be a combination of heuristics as well as machine learning models. And then after the prompt enhancer, we would have a prompt that actually is correct and is understandable. And it's not also vague. Now, this enhanced prompt goes into this response generator. This response generator is just the text generation decoding algorithm that we've went through. And it interacts with the trained LLM and generate the tokens one by one. And it could use some like top P sampling method. We'll talk about session management in a bit, but having that aside, after response generator completes its process, there would be some response to the prompt. And then that response goes into this response safety evaluator, or sometimes it's called output guardrails. So what it does, it again ensures that the generated output is also safe, meaning that it's not really sharing something dangerous or harmful or biased. And then if the result of this is that it's not safe, it would go again to the rejection response generator and generate a response that, hey, somehow we couldn't process your request or something like that. And if it determines that it's safe, it would just show the generated response to the user. So every time a user enters something like this, it would go through all these processes and components, and then the user would see the generated response. Now, if you see in chatbot services like ChatGPT, when you ask questions, you get responses. You can ask follow-up questions. And then the model would remember all the previous conversation and interactions. For example, you can ask something like, hey, help me come up with a name for my startup. And then the model would share something. And then you would say, hey, these are not good. Make it more formal or informal or something like that. And the model would remember everything from before, and then the model would adapt its response and show you another response. And this is handled by a session management. And all it does is basically it just keeps track of all the previous messages that were interacted between the user and the LLM. And it would append those into, and it's called chat history. It would append those to the new prompt each time. So each time you enter a text prompt and it goes here, right before that, it just appends here all the previous chats in that particular session. And all of this goes into the response generator. So when the response generator interacts with the LLM using top P sampling, the LLM takes into account the entire chat history when generating the new response. So this is how the follow-ups and chat and follow-up questions are handled using a session management. So that's it. That's about overall system design. Again, in practice, there are a lot of other components for different reasons. And again, it's something, there is not a single solution. Different companies use different components for different purposes. But this can be a rough, it gives an overall intuition of how a system design of a chatbot can look like. So with that, we can wrap up week 1 for LLM Foundations. We've learned everything we wanted to cover. And let me find this. So basically, we learned about LLMs. We saw pre-training, data collection, model architecture, training, text generation. And then we learned about post-training, in particular SFT and reinforcement learning, as well as reinforcement learning from human feedback for unverifiable tasks. And then we discussed evaluation and system design. So with that, now we built a strong foundation. And now we can switch to more advanced use cases and extensions of LLM that powers some of these applications.